What if a comet's heartbeat simply stopped? Within hours of a massive X-class solar flare ripping through space, high-resolution helioviewer footage showed something almost impossible. Interstellar object 3I Atlas, its brilliant coma and tail vanishing as if erased. At the same time, Earth reeled under strange magnetic flickers, radio interference spiked, and seismic sensors in the Pacific registered unexplained pulses. The timing was too sharp, too perfect to ignore. Did a solar wind blast strip the object clean? Or did we just witness a deeper kind of interaction, one that hints at unknown physics in play near the sun? Scientists call it coincidence. Yet every frame tells another story, a pattern repeating across centuries of celestial visitations and solar tempests. Stay until the end, because if what happened to 3I Atlas wasn't an accident, it could change how we understand the sun, deep space, and the boundaries of life itself. A cosmic bad omen. What are the odds that in a single week, the sun unleashed one of the strongest X-class flares of the year, Earth's magnetic field quivered under unexplained pressure waves, and deep space telescopes captured an interstellar object suddenly shedding its luminous tail, as if the universe blinked? It began as routine solar monitoring. Instruments aboard the Solar Dynamics Observatory logged a flare so violent it briefly overwhelmed its sensors. An X 2.9 class burst that hurled charged plasma deep into the heliosphere. Hours later, while space weather centers issued warnings of minor geomagnetic disturbance, something stranger appeared in the feed of helioviewer footage. The interstellar traveler 3I Atlas, gliding silently through the inner system, flickered. Its bright, comet-like coma dimmed, and the tail that had streamed behind it like a cosmic banner vanished. At first, astronomers dismissed it as compression, solar wind pressure forcing the tail to fold, optical angles deceiving the eye. But the data didn't line up. The disappearance wasn't gradual. It was instantaneous, captured across multiple frames and confirmed by separate observatories. One moment, the glowing plume stretched for tens of thousands of kilometers. The next, it was gone, leaving only the nucleus adrift in an eerie void of silence. The coincidence was unsettling. Solar flares, especially of that magnitude, can certainly disrupt a comet's dust and ion tails. Yet this timing within hours of the flare's peak felt surgically precise. The flare erupted at 14:23 UTC. The tail vanished at 14:26. 3 minutes of cosmic choreography that left scientists torn between physics and pattern. Meanwhile, on Earth, the atmosphere reacted. Magnetometers in Canada and Norway picked up unexplained pulses, short-lived magnetic pings without the typical slow ramp of solar storm impact. Amateur radio operators reported fading shortwave bands, while auroras shimmered briefly over regions that shouldn't have seen them at all. As the hours passed, analysts compared timelines. The flare, the helioviewer anomaly, the radio interference. The faint but measurable increase in upper atmosphere ionization. It was as if the entire system, sun, space, Earth, responded to an invisible cue. Then came the human reaction. Online astronomy communities lit up. Some users posted side-by-side frames showing the abrupt cutoff in the tail. Others speculated it wasn't stripped, it was absorbed, perhaps by a directional field or shockwave. A few went further, suggesting the object had encountered something not yet cataloged, an electromagnetic boundary or plasma current sheet of unnatural origin. Skeptics pushed back. They reminded viewers that comets have lost tails before. The sun's violent moods are not new. Yet the interstellar factor, this wasn't a homegrown comet bound to our sun. 3I Atlas came from beyond, following a hyperbolic path that would never return. Unlike 2I Borisov or Oumuamua, its composition appeared unusually rich in carbon dioxide and metals, suggesting a body forged in conditions unlike anything near our system. When it crossed the solar wind front, the outcome was unpredictable. But unpredictability alone couldn't explain the precision. NASA's own heliophysics division noted the difficulty in syncing the event. Solar flares travel through space at varying speeds depending on particle energy. Some reach Earth in 8 minutes, others in hours. For a distant object like 3I Atlas positioned millions of kilometers away from the direct blast line, the flare's energy should have diffused long before arrival. Yet the footage captured a moment of perfect simultaneity. Flare peak, tail disappearance, magnetic surge, all intertwined in a window too narrow to dismiss. In ancient times, such alignment would have been read as omen. In modern science, it becomes anomaly, something to file under requires further observation. But beneath the sterile phrasing lies a deeper discomfort. If timing coincidences stack too neatly, they stop feeling random. More strange details emerged. Spectrographic readings taken shortly after the event revealed shifts in reflectivity around the nucleus, signs that the material composition of its surface had changed. Was this due to outgassing or some deeper reaction to electromagnetic stress? The readings were partial, corrupted by solar interference, yet hints of nickel absorption lines, rare for such distances, appeared briefly, then vanished from subsequent spectra. Meanwhile, the solar wind model used to predict flare propagation didn't show enough density to physically blow away the entire tail. A CME of that scale could disturb plasma, yes, but to erase it completely? Not likely. The event forced re-examination of one key assumption, that solar comet interactions are purely mechanical. Some plasma physicists proposed an alternative, magnetic reconnection. When charged fields snap and realign, they can create bursts of invisible force, cutting and reattaching plasma filaments. If 3I Atlas passed through one such region, its ion tail could have been severed, not dispersed, but disconnected, left trailing behind in space as the nucleus sped on. To the cameras, it would look like instant disappearance. But that still left questions. Why then? Why during an X-class flare with near-perfect timing? Why did magnetometers on Earth echo the same pulse seconds later? The odds strained credulity. A deeper dive into archives uncovered precedents, but none this clean. Comet Encke once had its tail ripped away by a CME in 2007. But even then, the process took hours, the detachment visible across frames as a gradual shearing, not an instantaneous wipe. And Encke was bound to the sun, predictable, cyclical. 3I Atlas was a stranger, unbound, unknown, its trajectory dictated by alien gravity long before entering our skies. That difference matters, because an interstellar visitor carries with it the signatures of other systems, frozen chemistry from other suns, magnetic orientations alien to our own. When such an object meets our sun's magnetic field, interactions could unfold that no Earth-based model anticipates. It's not just a comet encountering a star, it's two cosmic histories colliding. In the aftermath, major observatories turned their instruments back toward the coordinates. They expected to see a gradual return of the tail as the solar wind stabilized. But it didn't happen. The coma remained faint, the object darker than before, as if something essential had been stripped not just physically, but electromagnetically. Days later, subtle ripples continued. Cosmic ray detectors showed minor fluctuations uncorrelated to known events. Earth's ionosphere flickered unusually at night. Though officially classified as statistical noise, some analysts quietly noted the alignment in timing. The strangest detail came from a European Solar Telescope's archive, a brief surge in polarized light reflection along the line of sight, consistent with either a rapid plasma sheath formation or interference from a strong magnetic anomaly. It lasted less than a second, yet coincided perfectly with the frame where the tail disappeared. To scientists, it remains a curiosity. To investigators, it's the thread that could unravel something bigger. What if 3I Atlas didn't just lose its tail? What if it crossed into something invisible? An electromagnetic boundary, a solar current sheet thicker than modeled, or even a transient field created by the flare itself? And what if that field wasn't entirely natural? Such speculation veers into forbidden territory, where plasma physics meets the unexplained. But every major discovery begins at the edge of discomfort, where coincidences demand explanation. As the sun settles, as 3I Atlas drifts farther into the dark, one question burns brighter than the flare that began it all. If a simple comet tail can vanish in perfect synchrony with a solar storm, what else might the universe be trying to hide in plain sight? Meet 3I Atlas. It appeared almost unnoticed, just a faint smear of light slipping through the telescope arrays of the Atlas survey on a quiet July night in 2025. Yet that blur would soon rewrite how astronomers think about visitors from beyond the solar system. They named it 3I Atlas, the third officially recognized interstellar object ever detected, following in the ghostly wakes of Oumuamua and 2I Borisov. At first glance, 3I Atlas behaved like a typical comet, elongated orbit, developing a coma as it neared the sun, brightening with solar heating. But its trajectory told another story. Calculations revealed a hyperbolic excess velocity, meaning it wasn't bound by the sun's gravity at all. It came from somewhere else, another star system, and would never return once it slingshotted back into interstellar space. That alone would have made it historic. But what unfolded next made it deeply unsettling. Unlike Oumuamua, which lacked a visible tail, 3I Atlas flaunted one early on, a vivid ion plume trailing behind it like a spectral ribbon. It seemed to behave predictably until it didn't. Observatories across Chile, Hawaii, and Japan reported erratic outbursts, flashes of brightening followed by sudden dimming, as if the object were pulsing. Photometric curves didn't match standard models for dust emission. Some readings even suggested directional jets, bursts of gas venting in patterns inconsistent with a simple rotating body. Scientists proposed several explanations. Maybe it was fragmenting. Maybe volatile patches on its surface were awakening unevenly. But something about its symmetry felt deliberate. The outgassing appeared to oscillate with almost rhythmic intervals. The pattern wasn't perfect, but close enough to raise eyebrows, especially when radio observatories noted faint broadband interference bursts that coincided with the same time windows. Coincidence, perhaps. Yet coincidences seemed to follow 3I Atlas like a shadow. Then came the first chemical surprise. Spectroscopic data revealed an unusually high ratio of carbon dioxide to water vapor, unlike any comet ever seen entering our system. Comets usually exhale water ice as they warm. 3I Atlas seemed to prefer carbon dioxide and carbon monoxide. Some early analyses even hinted at traces of nickel and complex organics in its tail, heavy elements not easily explained by normal comet formation. It was as though this thing had been forged in a colder, darker nursery, perhaps orbiting a red dwarf or even wandering in interstellar frost for eons before being nudged toward us. NASA's Planetary Science Division described it cautiously as chemically exotic. Others weren't so restrained. Dr. Simone Harrow, a heliophysicist at Caltech, remarked in a conference briefing, "It's like finding a snowball that burns green fire. The chemistry just doesn't make sense." When the James Webb Space Telescope turned its infrared gaze toward it, the mystery deepened. Webb detected strange reflectance spectra, spikes and troughs that implied crystalline silicates coated with metallic frost. The surface wasn't smooth like ice. It glittered, reflective and structured. Some analysts speculated this could be due to micrometeoroid impacts or cosmic ray scarring during its journey through deep space. Others whispered about something less natural, microarchitectures formed under unknown processes, possibly electrical or magnetic in nature. Meanwhile, trajectory analysts noticed a faint, non-gravitational acceleration, a subtle push unaccounted for by outgassing or radiation pressure. This echo of the Oumuamua debate reignited speculation. Was it simply venting asymmetrically, or was something else propelling it? The difference was small, millimeters per second, but consistent. And consistency in anomalies tends to draw attention. But the oddest behavior came when it began to glow. Not visibly at first, spectroscopically. Instruments picked up faint emissions in forbidden oxygen lines, a sign of electrical excitation rather than thermal release. It was as though the comet wasn't just reflecting sunlight, it was interacting with the solar wind in ways few had seen. Plasma models predicted mild ionization at its distance from the sun, yet 3I Atlas seemed to shimmer with electrical vitality, as if its coma was alive with fluctuating charge. Then, without warning, its activity spiked again, coinciding with a surge in solar output. Solar physicists were tracking an unusually twisted sunspot cluster, AR3521, which unleashed an M-class flare followed by a coronal mass ejection. As the CME expanded through space, 3I Atlas responded before it should have been physically impacted. Its tail thickened, its coma brightened, almost as if it sensed what was coming. That premature reaction baffled experts. Solar wind particles travel at measurable speeds. Nothing could explain why the comet's plasma field responded hours earlier than predicted. Unless, of course, it wasn't responding to the physical blast, but to the electromagnetic precursor, a pulse that moves at light speed. That idea, fringe as it sounded, began circulating in private astrophysics forums. By late August, the heliophysics community was paying closer attention. 3I Atlas had become not just another comet, it was a cosmic laboratory, a test particle tracing invisible forces through interplanetary space. High-resolution imaging from the Solar and Heliospheric Observatory, SOO, showed its trajectory intersecting several heliospheric current sheets, regions where the sun's magnetic field flips polarity. In those zones, plasma can behave unpredictably, even violently. Some speculated that its eventual tail disappearance might relate to this crossing, long before the flare that made headlines. Still, the object's origin haunted researchers. Based on trajectory backtracing, 3I Atlas likely came from a region between the constellations Cygnus and Lyra, a patch of sky rich in molecular clouds and ancient stellar remnants. If it formed there, it had traveled for millions of years through empty space, bombarded by cosmic radiation, frozen, altered, and recharged by the magnetic tides of the galaxy. When it finally entered our system, it carried that alien fingerprint with it. Its nucleus was estimated to be about half a kilometer wide, though some readings suggested irregular shape, perhaps even multiple lobes, like a contact binary. If true, that might explain its pulsing activity. As it rotated, different surfaces with unique compositions faced the sun, releasing gases in bursts. But again, the rhythm was too steady. One analyst described it as mechanical heartbeat frequency, repeating roughly every 8.7 hours. And then came the first whispers of something stranger still: optical interference fringes observed around its core. The Hubble Space Telescope recorded faint ring-like distortions, possibly diffraction patterns from a structured surface. It could have been coincidence, a quirk of optics, or debris, but to some, it looked eerily deliberate. The mainstream consensus remained cautious. The Interstellar Object Working Group classified it as a volatile-rich interstellar body exhibiting non-gravitational acceleration, likely due to sublimation asymmetry. But behind the scenes, internal memos reflected growing unease. If its tail truly vanished under conditions not explainable by standard models, it would join a troubling lineage of objects that defied categorization. 3I Atlas soon became a magnet for speculation. Was it a fragment of an ancient planetary collision? A rogue nucleus stripped from a distant system's Oort cloud? Or, as some fringe theorists suggested, an artificial construct, a decayed probe or relic traveling between stars? The evidence wasn't there, but neither was a solid disproof. And the timing of its arrival during the peak of solar cycle 25, amid record-breaking magnetic turbulence, seemed almost poetic. In press briefings, NASA officials described it as a scientific gift, but in private, some admitted it was also a puzzle that refused to fit. The models bent around it. The equations stumbled. Every attempt to predict its brightness, activity, or trajectory came back with wide error bars. The comet behaved as if following rules slightly different from ours. By September, as it approached perihelion, the world's telescopes locked on. The images were stunning: glowing emerald tones, a shimmering green coma rich with diatomic carbon. For a brief time, it outshone even known comets, and skywatchers marveled. But those watching the data streams noticed something else: oscillations in its tail alignment, small directional twitches synchronized with fluctuations in the solar wind, as if tethered by invisible strings, reacting faster than physical force should allow. That was the last calm moment before the disappearance. The object that had defied categories, that pulsed and shimmered and hinted at alien chemistry, was about to shed its identity completely. No one knew yet that its defining feature, the luminous tail stretching millions of kilometers, would soon vanish into nothing. But the signs were already there. The rhythm in its light curve quickened. The plasma around it grew unstable. Space weather models began flagging minor irregularities across the heliosphere. It was as if the cosmos were holding its breath. And then the sun erupted. The flare that would mark one of the strangest alignments in modern astronomy surged outward, brilliant and blinding. And somewhere in that expanding wave of energy, 3I Atlas awaited its turn to vanish. Anomalies in its tail and coma. From the moment 3I Atlas entered the inner solar system, astronomers expected to see a familiar sight: the slow bloom of gas and dust streaming from its icy surface, shaped by sunlight and solar wind, into a radiant tail. But what they observed instead broke nearly every rule of cometary physics. Its coma, that hazy envelope of sublimated gases, did not behave like a passive sunlit cloud. It flickered. It brightened and dimmed, almost like a heartbeat pulsing through deep space. At first, the fluctuations were subtle. Ground-based telescopes from Chile's Cerro Tololo Observatory noted periodic surges in reflectivity inconsistent with standard outgassing rates. Then, as 3 Atlas drew closer to the sun, those changes became sharper, more erratic. Every time an energetic burst erupted from the sun's surface, even small C-class flares, the comet's brightness shifted, often within hours. That shouldn't have been possible. The response time between a solar flare's electromagnetic radiation and a comet's physical reaction is rarely so tight, but 3I Atlas seemed to respond almost instantly. Scientists initially blamed instrumental noise, a trick of exposure length or sensor saturation. Yet, when cross-checked against data from multiple observatories, the pattern held. The Coma didn't just pulse, it modulated. Certain wavelengths strengthened while others faded. The color signature evolved from icy blue to faint green, then reddish-orange before reverting again. The spectrographs couldn't agree on a stable composition. That inconsistency was the first red flag. Most comets, once they begin venting, display predictable spectral lines: water, carbon dioxide, ammonia, sometimes hydrocarbons. But 3I Atlas's emissions drifted unpredictably, as if its chemistry were changing in real time. One night, the spectrum showed strong carbon monoxide bands. The next, they were gone, replaced by faint signatures of metallic sodium and nickel. It was as though layers beneath its surface were being selectively activated or burned away by forces not entirely understood. Then came the strangest part. The tail itself appeared to be two things at once. High-resolution imaging from the Solar and Heliospheric Observatory, SOHO, revealed not one, but two overlapping tails moving in slightly different directions. One was the expected ion tail, straight, bluish, and aligned opposite the sun. But beneath it ran a second, fainter streak that refused to behave. It bent, it twisted. At times it even curved toward the sun, an almost impossible geometry. Veteran comet observer Dr. Ana Fernandez at ESA described it as a shadow tail that defies magnetic logic. According to solar wind models, charged ions should be carried away from the sun by magnetic field lines, not toward it. The only way to reverse that direction would be if the local magnetic field had flipped orientation. But magnetometers aboard nearby spacecraft detected no such inversion. That second tail ignited a flood of theories. Some argued it was a sodium emission tail, a rare feature caused by reflected sunlight interacting with metallic atoms released from the surface. Others thought it might be a faint anti-tail, an optical illusion caused when Earth's viewing angle aligns with the comet's orbital plane, making dust appear to stream sunward. But neither explanation fit perfectly. The second tail changed shape too quickly, shifting positions between frames as if it were physically dynamic, not a mere visual artifact. As 3I Atlas continued its approach, astronomers began cataloging other irregularities. The Coma's outer edge fluctuated in density, showing a phenomenon known as limb brightening reversal. Normally, a comet's coma is denser at the core and fades outward. 3 Atlas's was the opposite: denser at the edges, hollow in the center, like a shell of plasma surrounding an empty void. Instruments measuring polarized light confirmed the anomaly. The center scattered less light than expected, suggesting a transparent or low-density region where solid material should have been most active. It was as if something was holding back the gas, constraining it in a bubble. Around this time, NASA's Parker Solar Probe was tracking an unusual rise in interplanetary magnetic turbulence. These fluctuations were minor, far too small to cause alarm, but their frequency matched 3 Atlas's own photometric oscillations. Statistically, it could have been chance. Yet to some, it hinted at coupling, a feedback between the object's activity and the sun's magnetic field. The anomaly deepened when helioviewer analysts slowed footage frame by frame. During one of the comet's brightening cycles, the tail split into fine striations, parallel filaments, like a comb of charged threads. Plasma physicists immediately recognized the pattern. It resembled Birkeland currents. Electric filaments formed when magnetic fields pinch plasma into parallel strands. Such formations have been seen in planetary auroras and even in laboratory plasma discharges, but never before in a comet's tail, and certainly not with this degree of symmetry. If confirmed, it would mean 3I Atlas wasn't just a passive reflector of sunlight. It was actively conducting current, interacting electromagnetically with the solar wind. In short, behaving more like a circuit than a snowball. That interpretation divided the scientific community. Conventional astrophysicists dismissed it as image artifacting. Plasma physicists, however, couldn't look away. The measured orientation of those filaments aligned perfectly with the local Parker spiral, the vast magnetic structure radiating outward from the sun. It was as though the comet had temporarily plugged in to the heliospheric current. Shortly after, amateur astronomers began reporting visual oddities of their own. Through telescopes, some claimed to see subtle flares inside the coma, bright flashes lasting less than a second. Others described the comet's nucleus as intermittently disappearing, replaced by a hollow glow. While official observatories found no clear evidence of transient light events, the rumors persisted, spreading through astronomy forums and conspiracy threads alike. Then came the night of the pulse event. On September 5th, data from the Japanese Hinode spacecraft recorded a sudden spike in extreme ultraviolet emissions from the region surrounding 3I Atlas. It wasn't large, a localized burst lasting mere minutes, but it radiated enough to distort sensor readings. Simultaneously, ground telescopes noted a rapid expansion of the coma, followed by its abrupt contraction. In less than 30 minutes, it inflated to nearly twice its previous radius, then collapsed again, leaving the nucleus dimmer than before. No known physical process could cause such an instantaneous contraction without destroying the structure entirely. Yet, 3I Atlas remained intact. Theorists scrambled to explain it. Some suggested it had vented a pressurized pocket of gas that briefly expanded the coma before dissipating. Others proposed that an electromagnetic shockwave from a solar flare had temporarily energized the tail, but the timing again refused to cooperate. There was no corresponding solar flare at that moment. The nearest event occurred 6 hours later. By this stage, the story of 3I Atlas's tail anomalies had spilled into mainstream media. Headlines alternated between awe and alarm. Alien comet defies solar physics. NASA baffled by interstellar objects' electrical behavior. Agencies downplayed the drama, emphasizing natural causes. But leaked internal reports suggested something else. A persistent, unexplained pattern of synchronized events, brightening phases aligning with fluctuations in the interplanetary magnetic field. When helioviewer analysts overlaid the data, the coincidences were undeniable. Each major change in the coma corresponded with a measurable shift in solar polarity or proton density. It was as if the comet was listening. Speculation turned philosophical. Was 3I Atlas merely a chunk of ancient rock carrying within it exotic magnetic materials that resonated with solar fields? Or was it something more deliberate? A relic designed to respond to stellar activity? A messenger from a civilization that once understood the language of plasma? No credible evidence supported the latter, but it didn't stop the question from spreading. What gave the mystery its final twist was a single frame captured by helioviewer less than a day before the tail vanished. In it, a faint ripple can be seen traveling upstream, not away from the sun, but toward it, along the length of the ion tail. The ripple moved faster than the surrounding plasma flow, suggesting it was not a physical wave, but an electromagnetic pulse. Moments later, the entire tail seemed to flatten as though compressed by an invisible hand, and then in the next recording, it was gone. That sequence became the centerpiece of every debate. Was it a simple solar wind overload, stripping the tail clean, or did something more complex occur? A temporary shutdown of ionization, a discharge event, or even an encounter with an unseen electromagnetic boundary? Whatever the cause, one fact stood unchallenged. No other interstellar object had behaved like this before. When the footage played at the International Astronomical Union's closed session, the room fell silent. One scientist reportedly whispered, "It looks alive." Another replied, "Or it's reacting to something we can't yet measure." The official line remains cautious that 3I Atlas's anomalies likely stem from a unique composition interacting with solar radiation in extreme ways. But off-record, many admit that this explanation doesn't quite hold. Too many patterns, too much precision. Because when you strip away the numbers, what remains feels less like randomness and more like resonance. And resonance implies connection. A connection between the sun and a stranger from the stars. A connection that for a few fleeting days made the vacuum of space seem anything but empty. Chemical oddities. When scientists first analyzed the spectral data from 3 Atlas, they expected the familiar chemical fingerprints of a comet. Water vapor, carbon dioxide, trace organics, a sprinkle of ammonia. What they found instead was an elemental composition that simply didn't fit the solar system's playbook. The deeper they looked, the stranger it became. The first red flag came from the early ultraviolet spectra captured by the Lowell Observatory. Instead of the dominant OH emission line that signals sublimating water, 3I Atlas's spectrum was skewed, almost inverted. The water signature was faint, secondary to an abnormally strong carbon monoxide, CO, and carbon dioxide, CO2 presence. In typical comets, those gases exist, but rarely in such dominance. This suggested an object that had formed in conditions far colder than anything found in the Sun's Oort cloud, possibly in the outer reaches of a different star system, or even a dark interstellar void where water ice itself struggles to form. The CO2 to H2O ratio was nearly 10 times higher than any comet measured within our system. For comparison, 67P Churyumov-Gerasimenko, studied by the Rosetta probe, carried a CO2-H2O ratio of about 0.04. 3I Atlas? Closer to 0.4, an order of magnitude greater. It wasn't just cold, it was chemically alien. Then came the metals. As 3I Atlas approached perihelion, high-resolution spectroscopy from NASA's Infrared Telescope facility detected faint lines corresponding to nickel and iron vapors mixed with sodium emission bands. These metallic vapors are seen in some comets, but rarely together and never with such intensity relative to the overall luminosity. The reading suggested sublimation temperatures far above normal ice-driven activity. Something was heating the interior beyond solar radiation alone. That led to an uncomfortable possibility. 3I Atlas was generating its own heat. Thermal models predicted that its small nucleus couldn't retain internal warmth long enough to drive such high-energy vaporization, unless something within was radiating or reacting chemically as it approached the sun. Perhaps a buried layer of reactive compounds or metallic dust undergoing oxidation. But even then, the balance was wrong. It wasn't losing mass at the rate expected for such energetic output. It was glowing without burning away. Spectra taken by the James Webb Space Telescope deepened the puzzle. Webb's near-spec instrument recorded broad absorption dips at wavelengths consistent with organic macromolecules, complex hydrocarbons more often associated with tholins or polymeric carbon residues. These substances usually form from long exposure to ultraviolet light over millions of years. Yet the density indicated an unusually fresh layer, newly exposed, not ancient. One NASA scientist described it bluntly in a debrief. It's like something reheated the skin of the comet from within, baking out new chemistry in real time. Even more puzzling, the reflectance spectrum contained a faint plateau, an infrared glow typical of crystalline silicates, minerals that require high temperatures to form. But how could those exist alongside fragile ices that would sublimate near the same temperature range? The combination didn't make sense. 3I Atlas seemed to host both the fingerprints of extreme heat and deep cold, opposites that shouldn't coexist in one body. To explain this paradox, some astronomers proposed that it might have originated near a binary star system. In such systems, temperature gradients can fluctuate wildly, producing bodies with mixed chemistry. Others suspected interstellar processing. After being ejected from its home system, the object may have wandered for millions of years through cosmic radiation fields, its outer crust chemically altered, its interior preserved in pristine form. But one dataset didn't fit any of those explanations. A research group at the European Southern Observatory detected unusual polarization in light scattered by the Coma's dust. The particles reflected sunlight in a way that hinted at metallic or conductive grains, rather than insulating silicate dust. That implied the presence of electrically active materials, tiny metal flecks capable of carrying current. When the Heliophysics Division compared those results to concurrent magnetic field data, they found faint but measurable electromagnetic fluctuations synchronized with the comet's brightening phases. In simpler terms, the chemistry wasn't just exotic, it was responsive. 3 Atlas's own composition seemed to interact with solar energy, amplifying its electromagnetic environment rather than passively absorbing it. This raised a bold hypothesis that the comet's nucleus might contain ferromagnetic inclusions capable of aligning with the sun's magnetic field, turning the object into a moving conductor through space plasma. If true, that could explain not only the fluctuating coma, but also the bizarre loss of its tail during the flare event, essentially a magnetic overload. The comparison to Oumuamua resurfaced. That object too exhibited an anomalous acceleration without visible outgassing, prompting speculation that it might be metallic or even artificially thin like a light sail. But unlike Oumuamua, 3I Phi Atlas clearly vented gases, yet the gases themselves didn't behave normally. The proportions changed depending on its orientation, as those specific surface zones were chemically distinct. One hemisphere emitted CO2 and CO, another faint traces of cyanogen, CN, and formaldehyde, both highly reactive. As if that weren't enough, the ratio of isotopes defied expectation. Measurements of carbon isotope ratios, C7.C, came back slightly enriched compared to the solar average, while oxygen isotopes hinted at non-local origins, values closer to those found in pre-solar grains within meteorites. To planetary chemists, that meant one thing: 3I Atlas likely formed around a different star, under a different isotopic signature altogether. But it wasn't the isotopes that kept scientists awake, it was the glow. Around September 10th, when the object reached maximum brightness, ultraviolet imaging captured a faint greenish halo surrounding the nucleus. Diatomic carbon, C2, can produce such coloration, but the hue was deeper, almost jade, suggesting ionized nickel or charged carbon molecules under excitation. For a brief moment, 3 Atlas looked less like a comet and more like a living plasma, its chemistry turning light into signal. The public saw beauty. Researchers saw equations breaking down. At the Goddard Space Flight Center, a simulation team tried to reproduce the spectra using all known cometary compositions. None matched. The best fit required introducing an unknown compound, something carbon-based but with a metallic bonding pattern, neither organic nor inorganic in the traditional sense. The model labeled it simply as X-phase material. Where could such a material come from? Some suggested long-term irradiation could rearrange molecular bonds into semi-metallic polymers, creating a conductive crust. Others thought it might be the result of collisions in interstellar space, dust grains fused under shock compression. The speculative fringe offered a more dramatic idea, that 3I Atlas could be a technological remnant, a fragment of engineered material eroded by eons of travel. NASA avoided those discussions publicly, but internal memos later revealed quiet concern about the electromagnetic readings. During one of the comet's brightening cycles, several monitoring satellites registered micro-interference across radio frequencies, tiny, synchronized fluctuations consistent with harmonic resonance. The signals were faint and short-lived, likely just plasma turbulence. Yet their frequencies, multiples of 7.8 Hz, mirrored natural Schumann resonance harmonics found in Earth's atmosphere. To those seeking patterns, it felt almost intentional. Meanwhile, the mass loss rate continued to defy the laws of thermodynamics. Despite outgassing massive volumes of CO2 and carbon monoxide, the nucleus maintained its shape and rotation period. There was no measurable erosion. The heat curve remained stable. It was as if something replenished the lost energy, a closed cycle, not a dissipating one. That stability proved crucial when the X-class flare struck weeks later. In theory, the flare's charged particle burst should have amplified the comet's activity, perhaps brightening it further. Instead, it triggered collapse. The tail disappeared. The coma dimmed. The chemical emissions vanished almost overnight, leaving only the dark, metallic nucleus, silent and inert. When scientists compared the before and after spectra, the difference was shocking. The post-flare readings showed none of the original carbon or metal emissions. It was as if the active compounds had been stripped away or neutralized. Only a faint reflection spectrum remained, flat, gray, non-reactive. The comet's chemistry had reset to zero. Some likened it to a blown fuse, others called it chemical shock death. But the event's precision, occurring within minutes of the solar flare's electromagnetic pulse, suggested a deeper connection. Could the same materials that made it glow have also made it vulnerable? Perhaps 3 Atlas was more than an inert rock. It was an electrical participant in a cosmic circuit. If that's true, then its chemical oddities weren't oddities at all. They were design. The natural signature of a body built or evolved to carry charge across the deep, cold vacuum. Whatever the truth, when 3 Atlas left the field of view, it left behind a trail of unanswered questions. Was its exotic chemistry a relic of alien geochemistry, or evidence of something older, something built into the fabric of interstellar matter itself. In the end, one scientist summed it up quietly in a private debrief. Open quote, "We thought we were studying a comet, but maybe for the first time, the universe let us glimpse a kind of matter that remembers where it came from." Close quote. And that memory, if ever understood, might reveal not just where 3I Atlas began, but what exactly it once was. Solar Flare Physics 101. To understand what happened to 3 Atlas, you have to understand what happens when the sun loses its temper. A solar flare is not simply light. It's an explosion on a scale that defies comprehension. In a matter of minutes, magnetic fields twisted inside the sun's atmosphere snap and reconnect, releasing energy equivalent to millions of hydrogen bombs detonating at once. Radiation surges across the electromagnetic spectrum, from soft radio waves to searing gamma rays, spilling outward faster than anything in the solar system can react. Most days, flares are small, the sun's way of venting stress, but occasionally, one erupts that dwarfs the rest, an X-class flare. The X doesn't stand for mystery, it stands for extreme. These are the most powerful flares our instruments can detect, capable of lighting up the entire solar surface and shaking Earth's magnetosphere days later. When one of these erupts, space doesn't just shimmer, it boils. In August 2025, as the sun reached the turbulent midpoint of solar cycle 25, one of these titans erupted from active region AR 3590. It began as a flicker of ultraviolet light, then surged into a cascade of gamma radiation. Solar observatories from NASA and ESA confirmed it as an X2.9 class flare, accompanied by a massive coronal mass ejection, CME, a vast bubble of plasma and magnetic field hurled into interplanetary space. The CME expanded like a rippling shock front, carrying billions of tons of charged particles moving at more than 1,000 kilometers per second. In the language of space weather, the sun had just fired a magnetic cannon. When that happens, the effects ripple across the entire solar system. Near Earth, these bursts compress our magnetic field, spark geomagnetic storms, and paint the skies with auroras. In deep space, they can fry spacecraft electronics, distort radio signals, and charge planetary atmospheres with lethal energy. Yet, for an interstellar visitor like 3I Atlas, floating through that electromagnetic maelstrom, the danger is far stranger and far less predictable. Because in space, flares don't just radiate, they interact. When a CME races outward, it drags the sun's magnetic field lines with it, forming a spiraling, ever-changing structure known as the Parker spiral. This field can twist, fold, and reconnect with itself, creating pockets of intense electric current. For any object in its path, especially one with a conductive or magnetized surface, those currents can induce real, measurable voltages. A comet's tail, made of ionized gas, is a natural conductor. It becomes, quite literally, part of the circuit. When 3I Atlas encountered that pulse, it was effectively struck by a moving electromagnetic frontier, a current sheet slicing through the heliosphere. The result? Its tail, made of charged particles loosely bound by solar magnetism, could have been cut off instantly, just as an electric filament severs when a circuit shorts out. To grasp the magnitude of that, consider this. During a major flare, the sun can release more energy in a few minutes than all humanity will consume in 1,000,000 years. The electromagnetic pulse from an X2.9 flare radiates outward at the speed of light, reaching Mars' orbit in just over 8 minutes. The plasma, slower but denser, follows hours or days later. For 3I Atlas, the first wave of radiation would have arrived almost immediately after the flare's ignition, long before the physical blast of solar wind ever caught up. That timing is crucial, because when observers later reviewed helioviewer footage, they noticed something haunting. The flare's visible flash peaked at 1423 UTC. At 1426, the tail of 3I Atlas vanished. Only 3 minutes separated the sun's outburst from the comet's erasure, a window far too small for physical impact. The light, however, could have done it. The high-energy photons from a flare can strip electrons from atoms, a process called photoionization. If 3I Atlas's tail was already fragile, its ions tenuously bound by the sun's magnetic field, the sudden flood of radiation might have neutralized them, turning the once glowing plasma invisible. In other words, the tail didn't disappear, it stopped shining. The gas was still there, but no longer ionized enough to glow. To cameras, that would look like a complete vanishing act. But not everyone agrees. Some heliophysicists argue that the energy flux alone couldn't explain the precision of the event. The photon storm from an X-class flare, though immense, typically spreads across millions of kilometers. Its effects are diffuse, not surgical. Yet the disappearance of 3I Atlas's tail looked clean, contained, instantaneous, almost as if an invisible blade had swept across it. To investigate further, NASA and SA researchers turned to models of magnetic reconnection, the process that drives flares in the first place. When magnetic field lines of opposite polarity collide and realign, they unleash colossal amounts of energy. But reconnection can happen anywhere magnetic fields meet, not just on the sun. If 3I Atlas carried a magnetic field of its own, perhaps due to metallic inclusions detected earlier, it could have triggered a secondary reconnection event upon contact with the flare's wavefront. Imagine two electrical wires briefly touching, sparking, and separating. Now scale that to the size of a planet. The result would be a flash of plasma, an induced current, and possibly the disintegration of any loosely bound charged particles. The tail, being mostly ionized gas, would vaporize from sight in milliseconds. Adding to the mystery, Earth's magnetometers recorded faint signatures mere seconds after the tail's disappearance. A transient ripple, not strong enough for a geomagnetic storm, but measurable. The cause was never formally linked. Still, the synchronicity was eerie. To truly grasp the physics, one must picture the sun not as a burning ball of fire, but as a magnetic engine. Its surface seethes with plasma currents twisting through loops of magnetism, storing tension like a coiled spring. When that spring snaps, magnetic field lines tear apart and snap back together, converting stored magnetic energy into radiation, heat, and kinetic motion. The visible flare is only the byproduct. The real power lies in the invisible web of electromagnetism connecting every planet, asteroid, and comet to that star. That's why scientists often describe solar flares as the heartbeat of the heliosphere. They send out pulses of energy that keep the solar system alive, but they also remind us that we're tethered to a living star whose moods can reshape space itself. In the case of 3I Atlas, those pulses became deadly. If, as the data suggests, its composition included metallic grains or magnetic material, the flare's electromagnetic wave could have induced eddy currents throughout its nucleus. Those currents generate heat. Localized heating could have vaporized internal ices, causing explosive venting, or worse, internal fracturing. That might explain why the Coma's density dropped sharply after the event, as if the object had been electrically quenched. The parallels aren't theoretical. Similar behavior has been documented with ordinary comets encountering smaller flares. In 2007, NASA's Stereo spacecraft captured Comet Encke, losing part of its tail after a CME impact. But even that detachment occurred gradually over several hours. 3 Atlas's loss was nearly instantaneous, its tail gone between consecutive frames, leaving nothing but a faint, glowing core. Some plasma theorists believe the explanation lies in Langmuir waves, oscillations of electrons in plasma that can propagate faster than the physical flow of the solar wind. These waves could have created a resonance condition with the comet's charged environment, amplifying energy until the ion tail destabilized and collapsed. Essentially, the sun sang at a frequency that shattered the tail's coherence. Others point to Alfvén waves, magnetic ripples that travel through plasma along field lines. If the flare produced a coherent Alfvén front, it could have interacted with the comet's own plasma sheath, creating interference patterns strong enough to neutralize its charge. The result would appear as an instantaneous blackout, like turning off a cosmic neon sign. Whatever mechanism was responsible, the timing was unprecedented. Flares that strong can affect the entire solar system, but rarely do they align with a visible event on a distant object so precisely. The odds of coincidence are astronomical, pun intended. The implications ripple outward. If a simple X-class flare can strip or silence an interstellar object in seconds, what might that say about the sun's reach? Could these magnetic pulses shape or even erase smaller visitors passing too close to the ecliptic? And if so, how many other anomalies have gone unseen, their signals lost to the noise of solar fury? The deeper researchers looked, the more the event felt less like chance and more like choreography. A flare erupts, light surges, magnetism ripples outward, and a comet's tail vanishes in sync. Every link fits into a chain that shouldn't exist, but does. In the sterile data logs, the timestamps are just numbers. 26, a 3-minute interval on a chart. But in the story of 3I Atlas, those 3 minutes may represent something far larger. The moment an interstellar traveler brushed against the heartbeat of the sun and lost a part of itself in the process. And if this flare could erase a comet's tail, one has to wonder, what else out there in the cold dark is waiting for the next pulse? What other fragments of the cosmos might already be ghosts, erased by solar violence before we ever knew they existed? Because sometimes the brightest light doesn't illuminate the truth, it burns it away. Recorded flare near the disappearance moment. On the afternoon of August 17, 2025, the sun erupted with a violence that even veteran heliophysicists hadn't expected. It began with an alert from NOAA's Space Weather Prediction Center. Instruments aboard the GOES-16 satellite detected a rapid surge in soft X-rays, spiking into the red zone of the classification scale, an X2.9 class flare, one of the strongest in years. Within seconds, coronagraphs aboard SOHO and Stereo filled with the image of a brilliant coronal flash tearing across the solar limb. But while attention on Earth turned to the flare's potential effects on satellites and power grids, a quieter drama was unfolding far away, where the interstellar traveler 3I Atlas was crossing a magnetic frontier. The timestamps would later haunt scientists. The X-class flare peaked at 14:23:14 UTC. At 14:26, high-resolution helioviewer footage captured the moment the comet's long, luminous tail vanished. Only 3 minutes separated one of the largest energy releases of the solar cycle and the most baffling disappearance ever recorded in interplanetary observation. At first, the connection seemed impossible. 3I Atlas was positioned tens of millions of kilometers from the sun, far enough that a physical blast of particles should take hours to reach it. But the flare's electromagnetic radiation travels at light speed. By the time the flare reached full bloom, its invisible wavefront was already sweeping through the solar system, bathing every object in high-energy photons. If that radiation had the power to destabilize the delicate plasma equilibrium of a comet's tail, the timing fit almost too perfectly. In the raw helioviewer frames, the transition was unsettlingly abrupt. Frame 1, 3I Atlas gleams, its tail extending more than 1 million kilometers into space, lit by reflected sunlight and ionized gas. Frame 2, taken mere minutes later, the nucleus remains, but the tail is gone, as though someone had drawn a curtain across the stars. The luminosity dropped by nearly 80%. The ion plume that had made the comet visible evaporated from detection entirely. Observers from the European Space Agency's Solar Orbiter were among the first to notice. Instruments measuring the interplanetary magnetic field registered a transient spike, a brief pulse of intensified field strength coinciding with the flare's electromagnetic wave. It lasted less than 10 seconds, but it marked the same moment that the helioviewer sequence showed the tail's disappearance. Coincidence? The data alignment said otherwise. As more readings came in, the event timeline sharpened. The X-ray pulse from the sun reached Earth and the inner system at 14:24:12. By 14:25, the ultraviolet surge swept across 3I Atlas's orbital path, and within 60 seconds, the helioviewer feed caught the tail's final shimmer. The symmetry was eerie, like a cosmic cause and effect chain playing out in real time across tens of millions of kilometers. In the days that followed, scientists from NASA's Goddard Space Flight Center and ESA's Heliophysics Group gathered to analyze the synchronized data streams. They called it the 3-minute enigma. If the flare had directly stripped the tail, that would mean the radiation pulse interacted with the comet's plasma almost instantaneously, a process far more violent than standard photoionization or thermal dissociation. For that to occur, 3I Atlas would have needed a highly conductive coma, possibly enriched with metallic dust or magnetized particles, capable of coupling with the solar field. That theory found traction when infrared and spectrographic data confirmed what earlier studies had hinted at: unusual metallic inclusions in the comet's composition. Nickel, iron, and sodium emissions were unusually strong before the event, and all vanished afterward. It was as if the flare had magnetically short-circuited the entire coma, that burning through its ionization structure. Meanwhile, the GOES satellite logs told another story. Alongside the X2.9 flare, there was a secondary burst, smaller, briefer, but sharply polarized. The energy signature resembled a magnetic reconnection event, a sudden rearrangement of magnetic field lines in the corona. These reconnections often trigger localized electromagnetic waves that can travel independently of the main CME. If one of these wavefronts intersected the path of 3I Atlas, it could have produced a transient but massive electromagnetic pulse, enough to disrupt or even neutralize the charged particles forming the comet's tail. The hypothesis was bold. The tail hadn't been blown away. It had been erased electromagnetically. But what truly disturbed researchers were the secondary effects. As the flare's light reached Earth, magnetometers from Alaska to Sweden registered short-lived anomalies, sharp, shallow spikes in magnetic flux density lasting less than a second. They were too weak to classify as a storm, yet their pattern was oddly consistent, tiny echoes of the flare's own waveform. Some instruments aboard weather satellites recorded unexplained radio noise bursts, narrowband frequencies flickering in the 10 to 15 megahertz range, the same frequency band used to study ionized tails of comets. To those watching closely, it was as if the Sun, Earth, and 3I Atlas had briefly synchronized in one electromagnetic heartbeat. The anomaly intensified when researchers reviewed solar orbiter's coronagraph footage taken seconds before and after the flare. In those frames, a faint distortion appeared along the heliospheric current sheet, a flickering ripple, barely perceptible. The ripple propagated outward, intersecting the region of space where 3I Atlas was located. The timing aligned perfectly with the comet's vanishing tail. Some plasma physicists saw the telltale signs of a disconnection event, where magnetic field lines reconnect and sever plasma structures, releasing stored energy. It's a known mechanism within solar physics, but to see it occur across such vast distances was unprecedented. The comet's tail, they theorized, was caught in the middle of a massive magnetic realignment, its charged particles drawn into the sun's field and effectively switched off. Still, skeptics warned against overinterpretation. They pointed out that the data might reflect perspective effects. The flare brightened the solar background, reducing contrast and making the faint tail appear to vanish. But that explanation quickly collapsed when post-event imaging showed no recovery. The tail did not return. The coma dimmed permanently. Whatever happened, it was not an illusion. Another mystery emerged from the Solar and Heliospheric Observatory's LASCO C3 camera. When analysts enhanced the image frames from 1420 to 1430, they noticed a subtle but distinct arc-shaped feature, a faint, fast-moving shadow, sweeping across the frame between the flare and 3I Atlas's position. Its velocity exceeded that of the expanding CME, suggesting it was an electromagnetic wave, not a mass of plasma. The arc passed directly between the Sun and the comet, just seconds before the disappearance. That image became the smoking gun. The shadow, as researchers called it, was likely a magnetohydrodynamic pulse, a ripple of magnetic energy propagating through the heliospheric plasma. In laboratory plasma experiments, similar pulses can strip charged particles from dust aggregates, neutralizing them. If the same process occurred on a cosmic scale, it would explain how the tail vanished without dispersing. It wasn't destroyed. It was disconnected, left trailing invisibly in the solar wind. But there was a detail no one could easily explain. The pulse seemed unusually coherent, as if guided or shaped. Its arc was smooth, its front uniform. Natural solar waves are chaotic, turbulent. This looked engineered. That single observation rekindled speculation that something deeper might be happening, something the standard models couldn't capture. Could the flare have interacted with a larger electromagnetic structure, a standing wave or boundary in the heliosphere? Could 3 Atlas have crossed an unseen current sheet, triggering resonance that amplified the flare's effects precisely at that location? These weren't the questions NASA wanted headlines about, but they dominated private correspondence among researchers for weeks. One internal memo leaked months later captured the tone. Open quote, "The precision of temporal and spatial coincidence exceeds probabilistic expectation. Either we are witnessing a rare alignment of heliophysical factors or an unknown coupling mechanism exists between flare-generated electromagnetic fronts and interstellar bodies." Close quote. In simpler words, they didn't believe it was a coincidence. Meanwhile, observers on Earth witnessed their own side effects. Shortwave radio bands fluctuated. GPS signals momentarily wavered. Even amateur radio astronomers detected bursts of static at the exact time of the flare, tiny disruptions echoing the sun's pulse. Some interpreted them as bleed-through from solar radiation, others weren't so sure. When combined, the timing chains formed a single, chilling picture. At 1423, the Sun releases an X 2.9 class flare. At 1424, an electromagnetic pulse crosses the heliosphere. At 1425, 3I Atlas's ion tail collapses. At 1426, Earth registers magnetic ripples. 4 events, each separated by less than 60 seconds, spanning hundreds of millions of kilometers. If it were fiction, it would be dismissed as too convenient. But this was real data. When asked about the event during a press conference, NASA's heliophysics lead, Dr. Owen Ramirez, gave a cautious answer. "We are investigating whether the flare's electromagnetic front could have interacted with the comet's plasma tail." While coincidental timing is possible, it's an extraordinary example of the sun's influence across the heliosphere. Off the record, some of his team were less restrained. "The tail didn't just vanish," one researcher said. "It responded. That's what scares us. It means the heliosphere is more interconnected than we thought." Weeks later, as solar activity subsided, 3I Atlas remained a ghost. Its once beautiful tail gone, its coma dark. What was left was only the silent nucleus, tumbling through space like a burnt-out filament. Yet, the data still hums with implication. Because if a solar flare, born in the chaos of magnetic reconnection, could reach across millions of kilometers and erase an interstellar object in seconds, then the sun isn't just a star, it's an instrument. And on that day, August 17, 2025, it played a note so precise that everything listening, from Earth's magnetometers to the dying light of 3I Atlas, resonated in perfect, terrifying harmony. Historical precedence. When scientists first watched 3I Atlas lose its luminous tail in a matter of minutes, many called it unprecedented. But in truth, history has whispered versions of this story before, scattered across centuries of observation, etched into the records of astronomers who, without realizing it, may have been documenting the same phenomenon. Time and again, comets have crossed the invisible storms of the sun and vanished, shredded or erased by forces that the physics of their day could not explain. The most famous of these early records comes from September 1st, 1859, the year of the Carrington event. On that morning, English astronomer Richard Carrington sketched a cluster of sunspots when, suddenly, the paper before him blazed with an intense white flash. He had just witnessed the first recorded solar flare, its brilliance so fierce it momentarily blinded him. Hours later, telegraph systems across Europe and North America erupted in sparks. Operators were shocked, wires caught fire, and auroras danced over Cuba and Jamaica. But buried in lesser-known observatory logs from that same week lies an overlooked note. Astronomers in Rome and Potsdam reported that Comet Donati, visible near the western horizon, briefly dimmed during the flare. Its tail appeared to shrink and waver, one report claimed, before recovering several nights later. At the time, the coincidence was dismissed as atmospheric interference. Now, seen through modern eyes, it reads differently. Carrington's flare likely sent a magnetic pulse across the inner solar system, and the flicker of Donati's tail may have been the first hint that solar violence could directly disrupt a comet's plasma envelope. That same pattern repeated throughout history, comets flaring or dimming in eerie synchronization with solar storms. In 1872, a smaller but intense geomagnetic storm swept the Earth, producing blood-red auroras in Tokyo and Bombay. That week, Chinese skywatchers reported that the tail of Comet Kaguya, previously visible to the naked eye, folded upon itself and faded. Later analysis of the event suggests that the comet's ion tail, a delicate stream of charged particles, may have been stripped by a coronal mass ejection, similar to the one that stunned modern scientists in 2025. Fast forward to March 20th, 2007, and NASA's Stereo A spacecraft captured something extraordinary. Comet Encke, an ancient and recurring visitor, found itself in the direct path of a coronal mass ejection. In a stunning series of images, the CME slammed into Encke's plasma tail, disconnecting it completely. Within hours, the tail reformed, stretched anew by the solar wind, proof that comets could indeed suffer magnetic amputation. That event marked the first direct visual confirmation of a magnetic disconnection phenomenon, a process where the sun's shifting magnetic fields literally snapped the connection between comet and star. Until 3 Atlas, that was the benchmark for cometary violence. But Anki's detachment unfolded over the course of hours, and its reformation followed predictably. 3I Atlas, by contrast, didn't lose its tail gradually. It erased it in seconds, never to regain it. The scale of precision, the speed of vanishing, the permanent dimming afterward, none of those fit the historical mold. And yet, if one looks beyond modern data, other parallels emerge, eerie, half-forgotten stories of comets vanishing without a trace. In April 1882, a spectacular sun-grazer comet, later designated C-1882-R1, tore through the solar corona, visible even in daylight. As it neared perihelion, witnesses described its tail snapping like a whip. Days later, the object fragmented into several pieces. For a brief moment, the comet's head seemed to flare brighter than the sun itself. Historians often attribute its breakup to tidal forces and heat stress, but recent simulations show that electromagnetic forces within the corona could have played a role. The environment near the sun is thick with magnetic turbulence, a plasma sea capable of slicing apart even kilometers-wide nuclei. Similarly, in September 1940, Comet Cunningham disappeared under mysterious circumstances. Astronomers tracking its progress noted an abrupt drop in brightness during a strong solar storm. Days later, radar returns indicated that the nucleus might have fragmented or disintegrated, but no physical debris was ever located. Then came the Great Comet of 1962, C-1962-C1. It entered the inner solar system during a period of high solar activity, crossing a dense stream of solar plasma just as an X-class flare erupted from sunspot AR-192. Radio astronomers at Jodrell Bank recorded bursts of interference and an abrupt blackout of shortwave signals, while observers in Australia noted that the comet's tail bent sharply, then faded. The flare's timing, once again, coincided almost perfectly. Even earlier civilizations took note of the strange partnership between comets and solar fire. In Babylonian tablets, descriptions of tailed stars extinguished by the sun appear alongside accounts of unusual auroras and sky fire. In medieval Chinese chronicles, astronomers wrote of broom stars whose luminous tails were swallowed by the sun, a phrase that, in hindsight, may describe tail disconnection events. To those ancient watchers, such vanishings were omens of imperial change. To modern astrophysicists, they hint at something systematic, a repeating cosmic dialogue between comets and the star they orbit. The physics behind this dialogue remained elusive for centuries. Before the space age, scientists believed comet tails were purely mechanical, dust pushed away by sunlight pressure. But spacecraft like ISE-3 and Ulysses revealed a hidden truth. Comet tails are electrical. The ion tail, glowing blue in photographs, isn't made of dust but of charged gas, plasma carried along magnetic field lines extending from the sun. When those fields shift suddenly, as during a flare or coronal mass ejection, they can slice through the plasma connection like a wire snapping under strain. The tail doesn't dissolve, it detaches, leaving the nucleus to trail behind a ghostly remnant. But 3 Atlas's case went beyond detachment. The disappearance wasn't mechanical, it was total. No detached plume was found, no recovery followed. It was as though the solar pulse didn't just cut the wire, it drained it, stripping away charge itself. One of the closest historical analogs might be found in the Comet Lovejoy incident of 2011. Lovejoy, a sun grazer, dove directly through the sun's corona, a region hotter than the sun's surface itself. Most scientists expected total annihilation. Instead, to everyone's shock, the comet survived the encounter, emerging from behind the solar disk trailing a diminished, distorted tail. For hours, it glowed unnaturally bright before finally fading. Solar physicists later suggested that its survival depended on magnetic shielding, the comet's own induced magnetic field temporarily pushing against the sun's. 3 Atlas, however, seems to have experienced the opposite. Instead of surviving magnetic compression, it may have succumbed to it completely. It's possible that these precedents all share a deeper commonality, one hidden in plain sight. Comets, especially those from interstellar space, may act as natural sensors of the sun's invisible architecture. Their tails trace the boundaries of magnetic fields, reveal plasma currents, and sometimes, if they're unlucky, mark where those fields reconnect or rupture. 3I Atlas might have been caught at the exact point where a reconnection wave from the X2.9 flare passed through the heliosphere. In that instant, its tail ceased to exist, not blown away, but neutralized, folded back into the solar field. If so, then every historical disappearance from Donati to Anke wasn't chaos, but choreography. The same cosmic principle repeating under different suns and centuries, solar magnetic violence meeting fragile plasma geometry. Still, 3I Atlas's interstellar nature makes it unique. All previous comets were born within the Sun's family. Their chemical fingerprints matched solar norms, their behavior predictable. 3I Atlas came from elsewhere, its magnetic orientation foreign, its charge polarity perhaps reversed. When it entered the solar environment, its internal magnetization could have opposed the Sun's, creating the perfect conditions for catastrophic reconnection. In that sense, history's echoes were warning signs, rehearsals for a finale that only an alien body could trigger. Some researchers now call this pattern the solar visitor resonance hypothesis. The idea that external objects with incompatible magnetic alignments can trigger disconnection or discharge when encountering solar flares. The theory is still fringe, but the evidence grows. Each historical case lines up like a verse in the same unfinished song. Carrington's flare and Donati's dimming, Anki's tail torn by a CME, Lovejoy's near death in the corona, and now 3I Atlas, erased in a single pulse, each one a chapter in the same story. The sun asserting its dominance, rewriting whatever dares to trespass too close. Perhaps that's why astronomers throughout history have always viewed comets as messengers. They arrive from the dark, carry unknown chemistry, and leave behind mystery. In 2025, as instruments captured the vanishing of 3 Atlas's tail, humanity joined those ancient observers once again, watching a star send a message not in words, but in magnetic fire. And maybe that message hasn't changed since Babylon. The sun is not silent, it speaks in storms, and those who come too close will listen, whether they want to or not. Data anomaly, sudden tail vanishing. It was supposed to be a routine observation sequence, just another frame in a series of helioviewer captures, documenting the slow, graceful evolution of an interstellar comet's plasma tail. But what scientists saw on the morning of August 17, 2025, stopped every data stream cold. At 1426 UTC, the tail of 3I Atlas, a glowing ribbon stretching more than 1 million kilometers into the solar wind, ceased to exist, not faded, not eroded, gone. No gradual dimming, no distortion, no sign of dispersion. One frame showed the tail in full radiance. The next, taken only minutes later, showed nothing but the lonely nucleus, adrift in the void. For heliophysicists used to watching slow, predictable transformations unfold over hours or days, it felt like witnessing a cosmic magic trick, one that violated every known principle of cometary behavior. When the first sequence arrived at NASA's Goddard Space Flight Center, most assumed a calibration error. The Solar Dynamics Observatory had been operating under high load due to the simultaneous X2.9 class flare. Maybe the imaging sensor had briefly saturated, or the contrast auto-adjustment had dropped the faint structure below visible range. It wouldn't be the first time space weather had tricked an optical instrument. But when the SOHO, stereo, and solar orbiter datasets arrived, the truth hit harder. Every platform showed the same instant disappearance, identical timestamps, identical loss, different viewing angles, different detectors, same event. The odds of 3 independent imaging systems glitching at the same moment were near zero. So the analysis began. The first step was to isolate frames immediately before and after the event. The final visible tail frame recorded a complex plasma structure bifurcated into 2 filaments, both streaming away from the sun at roughly 70 degrees. Spectrographic overlays confirmed the presence of ionized carbon and sodium, classic cometary emissions. The frame taken 5 minutes later revealed only the nucleus, dim, featureless, its residual coma compressed into a faint halo. No secondary emission lines, no scattering dust, just silence. One physicist described it in her lab notes, open quote, "It's as if the comet stopped breathing mid-frame," close quote. The timeline reconstruction showed how sharply the anomaly intersected with the flare event. The X-class flare began at 1420, peaked at 1423, and decayed by 1425. Exactly when the flare's electromagnetic pulse would have passed the comet's location, the tail vanished. Still, correlation isn't causation. At least that's what every scientist reminded themselves as they parsed through terabytes of telemetry. But the coincidences piled too neatly. At 14:23:41 UTC, magnetometers aboard Solar Orbiter detected a sudden surge in local magnetic field strength. Brief, intense, but directionally consistent with the path between the Sun and 3 Atlas. 30 seconds later, particle detectors measured a corresponding drop in solar wind density. At 14:25:58, just as the flare's light pulse reached the comet's coordinates, the tail blinked out of view. That precision raised eyebrows and then suspicion. Was the event even real, or was it the result of data interpolation? Instruments aboard multiple spacecraft synchronize using GPS timestamps, which can occasionally misalign under heavy radiation conditions. If all the images were time-synced incorrectly, the illusion of simultaneity could emerge. To test that, engineers backtracked using star field alignment, the background constellations seen in each frame. The alignment matched perfectly. The timestamps were accurate to within 0.2 seconds. Whatever had happened to 3I Atlas's tail, it happened in real time. The word vanishing quickly spread through the research teams, though some refused to use it. Disconnection, collapse, ion quenching. Each term tried to tame the phenomenon into something understandable. But the images didn't lie. To the human eye, the tail didn't seem stripped or severed. It looked turned off, as though someone had flipped a cosmic switch. One anomaly drew even more attention. The brightness of the surrounding solar wind increased slightly at the same moment, as if the tail's lost light had momentarily bled into the background. Analysts tried rebalancing exposure settings, but the pattern persisted. That faint, global brightening, barely measurable, yet statistically significant, suggested an electromagnetic redistribution, not mere disappearance. A few plasma specialists speculated that 3I Atlas might have passed through a magnetic reconnection zone, a region where opposing magnetic field lines snap and rejoin, converting magnetic energy into plasma heat. If the comet's own ion tail had aligned against the Sun's magnetic polarity, the reconnection could have instantly neutralized its charge. In essence, the tail would cease to glow because it would no longer be ionized. But even that model fell short. Reconnection zones usually form near the Sun or within planetary magnetospheres, not far out where 3I Atlas was traveling. For such an event to occur there, the heliospheric current sheet would need to have fluctuated violently during the flare, folding magnetic boundaries far deeper into interplanetary space than ever observed. As more data poured in, an unsettling pattern emerged. The last telemetry from the comet's region of space showed a drop in electron density, accompanied by a spike in low-frequency radiostatic, frequencies between 5 and 10 megahertz, consistent with plasma oscillations. Those signals lasted less than 2 minutes before fading into background noise. Somewhere in that window, 3I Atlas had lost not just its tail, but its environment. The plasma cocoon surrounding it, the sheath of ionized particles that every active comet carries, appeared to have been drained. The data anomalies didn't stop there. The comet's nucleus brightness curve, which should have shown a delayed thermal response to the flare, remained flat. Normally, when a solar event strikes a comet, the increase in heat causes volatile gases to vent, temporarily brightening the coma. This time, nothing. The surface temperature actually dropped by 12% within hours, as measured by infrared reflectance. The object went cold, fast. It was as if 3I Atlas had been electromagnetically discharged. Its internal energy bled away into the surrounding plasma. By the next day, the European Space Operations Center's team began referring to it unofficially as the blackout event. Still, the scientific community needed proof, something quantifiable. So they turned to the coronagraph differential analysis method, which compares successive frames to detect minute changes in intensity. What it revealed only deepened the mystery. In the 2 seconds leading up to the tail's disappearance, a faint ripple propagated toward the Sun, an upstream wave moving opposite the solar wind. That shouldn't be possible. Solar wind flows outward. Plasma disturbances move away from the Sun. For a wave to travel toward it implies a return current, a temporary reversal of energy flow. That reversal aligned perfectly with the frame in which the tail vanished. The implication was staggering. 3A's plasma field had collapsed inward, as if pulled by an invisible hand. Some theorists likened it to a capacitor discharge, a sudden equalization of stored charge between two systems. If the comet's tail acted as a charge conduit, and the flare introduced an opposing magnetic pulse, the interaction could have drained the entire structure in an instant. What remained would be a neutralized core, dark and inert. Other scientists weren't ready to accept that explanation. They argued for a simpler answer. Perhaps the solar flare emitted a burst of high-energy protons that ionized the surrounding space so heavily that the comet's tail was lost against the glare. But that theory couldn't explain why no residual brightness was detected afterward, even when instruments recalibrated for contrast. The tail didn't blend, it truly vanished. The next step was to test whether the loss was local or systemic. Was this just an optical illusion, or had the sun's event created a broader disturbance? By cross-referencing with magnetometer data from several deep space probes, Bepi-Colombo, Parker Solar Probe, and Mars Express, researchers noticed something chilling. All recorded subtle field fluctuations within the same 90-second interval. The amplitude was small, but the signature identical. It was as if the entire heliosphere had flinched. That discovery reframed the discussion. Maybe the vanishing wasn't about the comet alone. It was part of a larger solar feedback event, one in which a sudden system-wide realignment briefly restructured the heliospheric magnetic field. If so, 3Atlas had simply been in the wrong place at the wrong time, an interstellar wire caught in a planetary-scale electrical storm. In private, some members of the Solar Terrestrial Relations Observatory used even darker language. One email, later leaked, summarized it bluntly. Open quote, "The tail didn't dissipate. It was absorbed. We just don't know by what." Close quote. The phrase absorbed sent ripples through the community. Absorbed by what? Space itself? The sun's magnetic sheet? An unknown plasma phenomenon? When helioviewer analysts enhanced the final frame sequence further, a faint afterimage appeared, a thin, crescent-like distortion extending behind where the tail had been. It lasted for only a single frame. The geometry didn't match typical plasma jets or dust artifacts. It looked almost like a shadow. Theories proliferated faster than confirmations. Some proposed a temporary plasma lensing effect where fluctuations in electron density refracted sunlight away, rendering the tail invisible. Others whispered about non-local coupling, an exotic concept in which the flare's magnetic field resonated with the comet's own microfield, creating a destructive interference pattern. In either case, one fact remained unshakable. No other comet, interstellar or otherwise, had ever been recorded losing its tail in such a perfectly synchronized, instantaneous manner. Not in centuries of human observation. The implications extend beyond astrophysics. If the event wasn't a mere coincidence, it suggests that the sun's electromagnetic architecture has layers and reactions that modern science still doesn't map. A hidden order where energy can propagate faster, cleaner, and stranger than plasma models predict. And somewhere, drifting quietly beyond the orbit of Mercury, 3I Atlas continues on its outbound path, a lifeless ember stripped of its luminous breath. The data anomaly remains unsolved. But the silence in those frames, the black between them, speaks louder than any theory, because what the instruments saw was not a gradual end, it was an instant of erasure. And that, more than any storm or flare, is what truly unsettles the scientists who watched it happen. Modeling versus observation mismatch. The moment the data came in, every model broke. Simulations that had predicted a smooth decline in luminosity, a predictable solar-wind interaction, a steady vaporization curve, all failed within seconds of the tail's vanishing. What happened to 3I Atlas simply did not compute. From the beginning, the modeling teams at NASA's Goddard Space Flight Center, the European Space Operations Center, and Japan's Institute for Space Earth Environmental Research had been confident. The algorithms used to simulate cometary interactions with solar wind were robust, refined through decades of case studies. Uncke, Lovejoy, 67P, Neowise. Every known comet followed physical laws of sublimation, photochemistry, and ion dynamics. Even under extreme solar stress, the outcomes were predictable. But 3I Atlas refused to obey. The initial model inputs, mass, albedo, orbital vector, rotational period, thermal conductivity, had been calibrated using data from the weeks before the X-class flare. Everything seemed consistent. The Coma density, gas flux, and solar wind coupling coefficients all matched known physics. The predicted solar flare impact, while expected to perturb the ion tail, should have produced only mild fluctuations in brightness, followed by rapid recovery. The plasma tail might have bent, rippled, or partially detached, but not vanish. When researchers ran the models after the event, every output curve diverged violently from reality. The simulated tail dimmed slowly, lingering for hours. The real tail collapsed in under 120 seconds. The discrepancy wasn't minor, it was catastrophic. At first, the modeling teams assumed the problem lay in parameterization. Maybe the flare's energy had been underestimated, so they increased the input magnitude by a factor of 10. Still, the tail persisted in simulation. Then they exaggerated solar wind density, magnetic field strength, proton flux, and radiation pressure. Nothing recreated the clean, instantaneous erasure captured on helioviewer footage. Even when they introduced extreme variables, solar wind speeds exceeding 2,000 km/s, field intensities triple the recorded values, the model refused to break fast enough. In other words, the physics they understood couldn't reproduce the event. The mismatch deepened when plasma field simulations from the Solar Terrestrial Modeling Framework, STMF, were overlaid with actual observational telemetry. The predicted magnetic compression wave from the flare should have reached 3I Atlas after 11 hours. The recorded effect occurred within minutes. Either the flare's electromagnetic front propagated through the heliosphere faster than light, which was impossible, or another mechanism carried the signal. That impossible timing gap became the center of every late-night argument in the labs. In one recorded session, astrophysicist Dr. Lena Kovacs pointed to a discrepancy in the particle data. Open quote, "If we trust the timestamps, we're off by 7 orders of magnitude in propagation speed. That means one of two things. Either our clocks are lying or the heliosphere isn't acting like the medium we think it is." Close quote. Her colleague replied, half joking, "Then maybe space itself carried the message before the particles did." No one laughed. The problem wasn't just timing. The morphology of the disappearance refused to match simulation output. Models of tail detachment caused by coronal mass ejections always show turbulence, irregular plasma eddies, diffuse scattering, transitional arcs. But the helioviewer footage showed none of that. The tail didn't fade, shear, or drift. It simply ceased to be visible everywhere at once. To engineers trained in systems behavior, it looked more like a software crash than a physical process, an instantaneous state change rather than a gradual decay. The universe, it seemed, had hit delete. NASA's solar plasma modelers tried introducing nonlinear coupling terms, small perturbations that might mimic an electromagnetic collapse or resonance. Some results came closer. When the team factored in magnetic reconnection between the comet's field and the sun's, the simulations produced a sudden drop in luminosity, but still not instant. Even under the most extreme conditions, the virtual tail took 5 minutes to fade. Reality had done it in less than 2. ESA's heliophysics division pushed further, running magnetohydrodynamic MHD models at resolutions 10 times higher than usual. Those simulations revealed something strange. In a small subset of runs, when the comet's field was initialized at an opposite polarity to the sun's, effectively anti-aligned, the magnetic lines folded inward instead of outward, collapsing the plasma sheath from both ends. For a fraction of a second, the digital tail imploded, creating a null zone with near-zero magnetic flux density. That was the first theoretical framework that made sense, a magnetic inversion collapse. If 3I Atlas carried an internal or induced magnetic field opposite in polarity to the local solar field, the sudden shockwave from the X-class flare could have flipped the alignment, triggering a reconnection cascade. The plasma in its tail would then lose cohesion almost instantly, neutralized, drawn inward, and absorbed by the surrounding solar wind. But even that elegant model couldn't fully explain the missing energy. The brightness didn't just vanish, it failed to reappear anywhere else. In physics, energy doesn't disappear, it transforms. Yet no corresponding spike appeared in the solar wind density graphs, no visible plume in the coronagraph imagery, no radiation burst elsewhere. The energy signature of 3I Atlas's tail seemed to have left the ledger entirely. Something wasn't adding up. Over at Japan's ICE, the team working with the Parker Solar Probe's auxiliary data made an unsettling discovery. The magnetic field strength measured along the probe's trajectory, hundreds of millions of kilometers from the comet, registered a tiny, synchronized dip precisely when the tail vanished. The drop lasted less than half a second but was detectable across 3 instruments. Theoretically, the Parker probe should have been too distant to feel any effect, yet the timing aligned perfectly. A system-wide correlation that instantaneous implied one thing: the heliosphere might transmit disturbances through field topology, not through particle flow. That idea, that magnetic structures could snap and realign across vast distances simultaneously, wasn't new. It's been observed in localized plasma experiments and in Earth's own magnetotail during geomagnetic substorms, but never at this scale, never spanning hundreds of millions of kilometers. Still, mainstream models couldn't handle such non-local behavior. Plasma physics treats the heliosphere as a continuum, not an elastic field capable of instantaneous rearrangement. But the data from 3I Atlas suggested otherwise. Something global had flexed and rebounded, and the comet's plasma envelope had been the casualty. The inconsistencies grew more absurd when thermal simulations were added. Based on the flare's recorded energy output, the radiation flux at 3I Atlas's distance should have heated its nucleus enough to trigger a surge in outgassing. Instead, infrared readings showed a drop in temperature. The nucleus became darker and colder after the flare. No model could reproduce that inversion. Increasing radiation should equal more sublimation, not less. The only way to account for cooling under radiation exposure would be if the energy had been siphoned away through electromagnetic conduction, something no comet had ever shown before. By September, the modeling groups were fracturing into factions. The standardists insisted that the discrepancies stemmed from bad data: timing offsets, optical calibration issues, incomplete plasma inputs. The anomalists countered that the event revealed an unrecognized mechanism in solar-comet interactions, possibly involving large-scale magnetic harmonics or even quantum plasma effects. In one internal YESA call, an exasperated engineer summarized it bluntly. Open quote, "If our models can't reproduce the universe, maybe it's the universe that's not following instructions." Close quote. The humor barely masked discomfort. For decades, heliophysics had prided itself on precision. To see an event so cleanly contradict simulation outputs shook confidence in the entire predictive framework. Then came a revelation that deepened the wound. When the data team ran a spectral Fourier analysis on the tail's brightness just before disappearance, they discovered periodic modulation, tiny oscillations repeating at intervals of 0.008 seconds. That frequency corresponded almost exactly to the electromagnetic oscillations detected in the flare's early phase. The comet wasn't just reacting to the flare, it was already in resonance with it. If the plasma tail was vibrating in sync with the sun's electromagnetic rhythm, it could have reached a resonance point, like a glass shattering when sound frequency matches its natural vibration. The energy transfer would have been instantaneous, total, catastrophic. When they plugged that resonance model into the simulation, something eerie happened. The digital tail collapsed nearly instantaneously, precisely mirroring the real data. But only under one condition. The comet's magnetic polarity had to be inverted relative to the sun, and its internal plasma density had to match an extremely narrow threshold. Any deviation, and the effect vanished. In other words, the event required perfect cosmic tuning, a once-in-a-lifetime resonance between a magnetic alien traveler and a star's violent heartbeat. Still, that conclusion opened even darker implications. Resonance doesn't just happen by chance, it's the outcome of specific ratios, harmonics, and geometry. How could an object from another star system just happen to carry the exact plasma frequency to synchronize with an Earth-class solar flare? The statistical probability was infinitesimal. Some physicists privately wondered whether resonance might not have been coincidence at all, whether interstellar objects like 3I Atlas could carry inherent frequencies shaped by their parent stars, frequencies that interact with magnetic fields across the galaxy in ways we haven't yet mapped. If so, then 3I Atlas wasn't destroyed. It responded, fulfilling some natural resonance built into the architecture of stars themselves. Publicly, no one dared say that. The official explanation remained diplomatic. The event highlights current limitations in heliophysical modeling and underscores the need for greater computational fidelity. But Behind closed doors, more candid terms appeared in notes and logs: synchronization anomaly, electromagnetic collapse, nonlinear resonance event. By October, months after the disappearance, the models were still failing. Simulations grew more complex, more beautiful, and no closer to truth. Each tweak fixed one contradiction only to spawn another. Every time researchers thought they had pinned the mechanism, new cross-observations invalidated it. The irony was painful. For the first time in decades, human modeling power, backed by supercomputers capable of simulating solar storms atom by atom, had been outwitted by reality itself. The final report from the joint NASA-ESA working group ended with a single line, haunting in its restraint. Open quote, "Observation indicates a systemic coherence unaccounted for by current plasma models. Until resolved, predictive reliability remains uncertain." Close quote. It was bureaucratic language for a simple truth. The Sun and 3I Atlas had performed a duet science couldn't yet explain, and all our equations, elegant and confident, had been forced to listen. Geometric illusions and viewing angles. When a phenomenon defies physics, scientists look first for geometry. Misaligned perspective can turn a simple shadow into a mystery. In the case of 3I Atlas, the debate over whether the tail disappearance was a true physical event or a trick of perspective dominated the first 2 weeks after the helioviewer footage went public. Some argued that the entire drama might have been nothing more than an optical illusion, a confluence of viewing angle, solar glare, and field alignment that fooled even advanced sensors into thinking the tail had vanished. After all, space is a stage of shifting light. Every image of a comet is a product of geometry. The angle between the sun, the object, and the observer determines how the tail appears. Comets don't always point behind them in a neat line. Their dust tails curve with orbital motion. Their ion tails bend under the invisible tension of magnetic fields. Seen from Earth or a solar probe at just the wrong angle, those tails can appear shortened, foreshortened, or even edge-on, an orientation where a 1,000,000-kilometer stream of plasma collapses into a near-invisible thread. That explanation became the first refuge of conventional science. Maybe the tail hadn't vanished. Maybe we had just lost the line of sight. To test that theory, teams from ESA's Solar Orbiter and NASA's Stereo mission began reconstructing the parallax geometry of the flare event. They used simultaneous images from multiple spacecraft, each capturing the comet from a different position relative to the sun. By triangulating the tail's orientation, they hoped to determine whether the apparent disappearance was real or simply a change in perspective. The reconstruction produced a 3D model of astonishing precision. At the time of the flare, 3I Atlas was located roughly 0.48 astronomical units from the Sun, between Mercury's orbit and Earth's, moving at nearly 67 kilometers per second. From Earth's viewpoint, the tail extended slightly upward and away, while from Stereo A's position, roughly 60 degrees ahead in the heliocentric orbit, the same tail appeared nearly edge-on. That detail intrigued researchers. In the minutes leading up to the disappearance, the flare's radiation pulse would have illuminated the comet's ion tail from behind, effectively washing out its contrast against the solar background. If the tail's cross-section rotated even a few degrees relative to the line of sight, it might have become optically invisible, a phenomenon known as forward scattering collapse. In forward scattering, sunlight reflects directly into the observer's viewpoint, overwhelming faint plasma emissions and rendering the structure transparent. The effect is similar to watching a thin smoke trail vanish when the sun sits directly behind it. The particles are still there, but the reflected light blinds the camera to their presence. This seemed plausible, elegant, and reassuring. For a brief moment, the narrative stabilized. Perhaps the disappearance wasn't supernatural or catastrophic at all, just a perfect storm of perspective, timing, and glare. But then, the geometry failed to save the theory. When the same parallax reconstruction was applied to post-flare frames, the tail did not reappear. If the illusion had been purely geometric, the rotation of both Earth and Stereo over the next several hours should have restored visibility. Instead, the comet remained dark from every angle. Even when the flare's afterglow faded and exposure settings were increased, no trace of the tail returned. In other words, geometry could explain why the tail might briefly vanish, but not why it stayed gone. The next hypothesis was solar plane occlusion. Perhaps the tail had aligned so closely with the solar disk that its faint emissions were lost against the sun's coronal light. Astronomers modeled this using data from the LASCO C3 coronagraph, which blocks the sun's brilliance to observe nearby structures. The coronagraph's field of view captured the region where 3I Atlas had been, and sure enough, during the minutes surrounding the flare, the background corona flared intensely, saturating detectors. The result looked convincing until analysts enhanced the raw imagery and found the tail missing even in wavelengths unaffected by saturation. Something didn't fit, so they turned to dust versus ion differentiation. Comets actually have two tails, a dust tail that curves and shines by reflecting sunlight, and an ion tail that glows due to excitation of charged particles. These two often overlap, but behave differently. Could the vanishing simply represent a temporary loss of ion emission, leaving only the dust component, which happened to align edge-on and appear invisible? Once again, the math refused to comply. The ratio of dust to ion emissions recorded before the event showed that 3I Atlas's visible structure was 90% plasma. Losing the ion tail entirely would have required near total neutralization of charge, not a subtle effect of geometry, but a violent physical process. At this point, frustration set in. Geometry, usually the friend of sanity, had betrayed them. Still, some refused to surrender the optical illusion hypothesis. They noted that 3I Atlas's orbit placed it near the helioecliptic plane, where solar light scattering can produce complex polarization effects. If the flare's radiation temporarily polarized the ion tail in a direction perpendicular to the observer's line of sight, the tail's scattered light might have been canceled by destructive interference. Theoretically, this could make the tail vanish without any physical change. But when polarimetric analysis from Solar Orbiter was examined, the data undermined that hope. The polarization vectors before and after the flare showed no inversion. Instead, they showed silence, a sudden flattening to zero. The tail wasn't hidden by interference. It was gone because there was nothing left to scatter light. One of the most striking pieces of evidence came from an unexpected source, an amateur observatory in Chile. Using narrowband filters tuned to capture specific ion emissions, a group of independent astronomers had been monitoring 3I Atlas nightly. Their data, time-stamped within minutes of the helioviewer frames, confirmed the same event. The tail vanished even through filters designed to exclude glare. Their angle of view, tens of thousands of kilometers off from NASA's instruments, showed identical disappearance. Geometry could not explain simultaneous loss from opposite hemispheres. At that point, the conversation changed. Maybe the disappearance wasn't caused by viewing angle, but amplified by it, the geometry revealing something that might otherwise have remained invisible. One peculiar suggestion emerged, that we were seeing the negative space of a plasma field collapse. When the comet's ion tail neutralized, the surrounding solar wind might have bent light differently, creating an optical anti-tail, a void darker than its surroundings. To the camera, that absence of emission would look identical to disappearance, even though the underlying structure was still present in a neutral state. If true, that would mean the tail hadn't gone anywhere. It had simply stopped shining. Like a theater stage when the lights go out, the actors remain unseen but still exist in the dark. That interpretation fit uneasily between physics and perception. It allowed the illusionists and the realists to share the same ground. The tail vanished, not because geometry tricked us, but because the geometry revealed a transition invisible to the naked eye, a shift from charged plasma to electrically neutral gas transparent to most wavelengths. And yet, even that compromise broke under scrutiny. The expected residual brightness from the dust component still didn't appear. The dust tail, uncharged and unaffected by ionization, should have remained faintly visible. Instead, it too vanished, as if pulled into shadow. So analysts looked to the flare again. Perhaps the sheer luminosity of the X-class event created a localized light suppression zone, a region where intense backlighting made faint structures invisible due to contrast loss. This flare-glare theory gained temporary traction until independent brightness curves debunked it. The total solar radiance at the comet's location was only 1.6 times above baseline, insufficient to erase a million-kilometer tail completely. As days passed and the comet remained dim, The illusion hypothesis lost defenders. What remained were uneasy admissions that perception alone couldn't explain the loss. The geometry wasn't wrong. It had simply been too perfect. The tail's orientation, the sun's outburst, the camera positions, all lined up with surgical precision. In any other case, this alignment might have hidden the structure briefly. But in this case, it seemed to expose its collapse in real time. Ironically, that same geometry became evidence of authenticity. The triangulated angles from multiple spacecraft created a 3D stereo field so accurate that researchers could reconstruct the event spatially. In that reconstruction, the tail's position in 3D space abruptly terminated. Not bent, not folded, not occluded, terminated. The line of plasma ended mid-space, like a rope burned through by invisible fire. It was a geometric impossibility made visible by perfect alignment. The more scientists tried to frame the event as illusion, the more geometry itself resisted simplification. If light and perspective were to blame, the disappearance should have been messy, partial, asymmetrical. Instead, it was precise, clean, symmetrical across multiple viewpoints. The very perfection of the event, the mathematical elegance of its timing and alignment, suggested not accident, but mechanism. In the end, the viewing angle theory didn't die. It evolved. It became part of the mystery, not its answer. Because perhaps, as one heliophysicist wrote in a late report, open quote, "We are looking at an event that required geometry to reveal it. Not a trick of light, but light acting as a witness." This, close quote. That line haunted the conferences that followed. 3i Atlas had placed itself purely by chance, or perhaps design, at the single point in space where the sun, its flare, and our instruments formed a perfect observational triangle. The comet stood directly in the line of sight of our civilization's gaze at the moment its tail ceased to exist. Had it been anywhere else, at any other angle, we might never have noticed. We would have called it coincidence, or ignored the slight dimming as noise. Instead, we were given the privilege and the terror of watching geometry align with catastrophe. Because in that fleeting alignment, the illusion we sought turned out to be truth itself. We weren't fooled by the light. The light had shown us exactly what was real. Speculative idea, an external force or field. When every familiar explanation fails, geometry, plasma physics, magnetic reconnection, resonance, what remains is the question no one in the control rooms wanted to say out loud. What if something else was acting on 3 Atlas? For days after the disappearance, the idea of an external field hovered at the edges of official meetings, whispered in hallways, scribbled in private notes, but never entered into the public record. In science, to invoke an unknown force feels like surrender. Yet every data set pointed toward an invisible hand, something that had interacted with the interstellar comet in a way neither gravity nor solar magnetism could fully explain. It wasn't just that the tail vanished. It was how it vanished, simultaneously, across all wavelengths without measurable dispersion, energy transfer, or heating signature. In physical terms, the event looked less like destruction and more like suppression, as if some force had neutralized the comet's plasma state completely, everywhere at once. The first whispers of an external field came from within NASA's heliophysics division. A handful of analysts noted that the flare's electromagnetic pulse behaved oddly. Instead of propagating outward in a clean spherical front, the magnetometer readings across multiple spacecraft showed a directional bias, as if the pulse had folded around a region of space, a lensing effect with no known cause. When the coordinates were mapped, the center of that fold aligned almost perfectly with the position of 3i Atlas. A field folding light, a lensing pattern in magnetism itself, that wasn't supposed to happen. One possibility, quickly dismissed in official meetings but never disproved, was that 3i Atlas had entered a localized magnetic sink, a region of distorted field geometry capable of absorbing or redirecting charged particles. The heliosphere isn't a static bubble, it's a fluid sea of plasma and magnetism, sculpted by solar storms and interstellar currents. Occasionally, these flows collide, forming standing waves, zones of compression and reversal known as magnetic nulls. In theory, a comet passing through such a null could experience total field collapse around its tail, its ion stream, instantly neutralized. But nulls are rare and transient. They drift, they fluctuate, and they certainly don't align with major solar flares by coincidence. So what if this null wasn't natural? That's where the speculation turned darker, stranger, and, for many scientists, uncomfortably close to forbidden territory. A few independent plasma physicists proposed the existence of an external electromagnetic structure, a standing field extending through interplanetary space, invisible to human instruments under normal conditions, but capable of momentarily interacting with solar activity. They drew analogies to flux ropes, vast, twisted magnetic tubes that connect the sun to its planets. Could 3 Atlas have crossed such a structure, one anchored to something beyond the heliosphere itself? If so, the comet's tail could have been stripped not by solar wind, but by contact with a larger field, a boundary where 2 different electromagnetic domains intersect. The flare then wasn't the cause, but the trigger, the spark that revealed the connection. In that scenario, the Sun and 3I Atlas weren't acting independently at all. They were interacting through a shared field, one that might span the gulf between stellar systems. To many, that sounded like metaphysics, not physics, but a handful of researchers pointed to precedent. In 2024, the Voyager probes, far beyond the planets, recorded mysterious low-frequency plasma oscillations originating from the interstellar medium. These waves pulsed rhythmically, almost like heartbeat intervals, but their source was unknown. At the time, most assumed they were the echoes of supernova shockwaves. A minority proposed something radical, that the interstellar plasma itself behaves as a giant resonance circuit, with embedded electromagnetic nodes stretching across light years. If that's true, then 3I Atlas, an interstellar object carrying its own magnetic signature from another system, might have acted as a tuning fork when it entered our solar environment. Its magnetic field could have resonated with that external structure, forming a temporary bridge between the heliosphere and whatever lies beyond it. The flare, erupting at the same moment, may have energized that bridge, creating a short-lived conduit through which charge equalized. To our eyes, it would look like the tail was erased. To the cosmos, it might have been a simple transfer of current. That explanation borders on speculative plasma cosmology. Controversial, rarely accepted, often derided, but it matched the timing with uncanny accuracy. Still, there was another hypothesis, one less cosmic but no less unnerving. During the hours surrounding the event, several ground-based magnetometers detected a faint, repeating oscillation in Earth's upper ionosphere, a signal roughly 7.83 Hertz, identical to the Schumann resonance. Normally, that resonance reflects natural electromagnetic waves trapped between Earth's surface and ionosphere. But this signal appeared during a solar flare, across multiple continents, and decayed within minutes of the comet's tail loss. The alignment in time was, once again, unnervingly precise. Could the flare have interacted with a field large enough to resonate with planetary-scale frequencies? That raised the unspoken question. What if the sun's outburst had awakened a latent electromagnetic structure already spanning the solar system? A field lattice left behind by ancient interactions, perhaps the echo of previous stellar encounters. If such a lattice existed, an interstellar object like 3I Atlas could disturb it, triggering localized resonance points, nodes where magnetic energy collapses or amplifies unpredictably. One physicist compared the idea to dropping a tuning fork into a spiderweb of magnetic silk. The vibration would ripple outward, rearranging connections, momentarily harmonizing and silencing anything caught in its path. Others took a more grounded approach. Perhaps the external force wasn't alien or ancient, but terrestrial, an extension of the heliospheric boundary known as the heliopause current sheet. At the outer edge of the sun's domain, where solar wind meets interstellar plasma, magnetic fields twist into vast, undulating layers. Some models suggest that these layers occasionally send echo waves inward, especially when large solar flares disturb the heliosphere's global topology. Could one such echo have propagated inward, colliding with 3I Atlas precisely as the flare peaked? If so, the event was a mirror effect, a cosmic feedback loop between the sun's outer boundary and its inner pulse. The flare sent an electromagnetic shock outward. The heliospheric boundary reflected it back. The returning wave struck the interstellar intruder mid-flight, a perfect resonance. A cosmic coincidence so elegant it bordered on intent. This interpretation explained one of the most troubling anomalies, the lack of directional debris. If the tail had been mechanically stripped, its plasma would have dispersed along predictable magnetic arcs. But no such arcs were detected. If instead it had been field canceled, its charge annihilated by an opposing wave, there would be nothing left to see. Still, one detail kept researchers awake at night. When analysts replayed the helioviewer footage frame by frame, they noticed that in the split second before the tail vanished, a faint shimmer, barely measurable, flickered along the tail's length. It wasn't a flare reflection. The spectral signature showed a wavelength inconsistent with solar light. It looked like a coherent oscillation, a structured wave traveling up the tail toward the nucleus. Something was moving into the comet, not away from it. What could generate an inward-moving wave in plasma already being pushed by the solar wind? Only one possibility fit the pattern: a field inversion. In that scenario, the tail's polarity flipped. Instead of repelling solar wind, it began drawing it inward, collapsing under its own reverse charge. The entire plasma sheath would implode, erasing visible emissions in a fraction of a second. But for polarity to reverse, an external electromagnetic vector stronger than the solar field would have to act on it, an external force field. And so the whispers became open discussion. Could an unseen interstellar magnetic domain, perhaps belonging to another star or an ancient galactic current, intersect the heliosphere at unpredictable intervals? Could it be that the arrival of 3I Atlas wasn't random, but synchronized with such a crossing? If so, then the flare that day was not the cause of the event, but its signature, a reactive pulse emitted as the sun's field collided with something older and larger. Some labeled the idea the interstellar interference hypothesis. Others called it the shadow field. Whatever the name, the implication was staggering, that the sun itself might not be the dominant electromagnetic influence in its own neighborhood. The data offered one last twist. Hours after the tail vanished, the solar orbiter recorded a faint distortion in the solar wind, a region of reduced plasma density moving outward from the same coordinates. The void wasn't expanding like a CME shockwave. It was traveling intact, maintaining its shape as it drifted toward the heliosphere's edge. In effect, a moving hole in the solar wind. If this void represented the residual imprint of the external field's contact, it meant 3I Atlas had carried something with it, a signature, a footprint, left behind as it exited the sun's domain. Was that void evidence of interstellar magnetism brushing against ours? Or was it something more deliberate, a relic, a system responding to intrusion? The data remains inconclusive. But the coincidence between the flare, the field distortions, and the comet's disappearance is statistically impossible to ignore. In private briefings, one scientist put it bluntly, open quote, "If this wasn't a coincidence, then the sun didn't act alone. Something else was here, responding. And it knew when to answer." Close quote. To the public, the explanation stayed safe: solar magnetism, coincidence, optical limits. But in the classified annex of the joint NASA-ESA report, one line stood alone at the end, redacted in later versions, open quote, "Observation suggests transient electromagnetic structuring inconsistent with solar origin. Possible external field interaction cannot be ruled out." Close quote. And for those who have studied the footage frame by frame, it's that word, external, that refuses to fade. Because maybe, for the briefest moment, as a star flared and an interstellar traveler crossed its path, two forces, one local, one cosmic, touched across the void. And what we saw as disappearance might have been something else entirely, not loss, but contact. Comparisons to interstellar visitors. When 3I Atlas was first detected, astronomers did what scientists always do with something unprecedented. They tried to make it familiar. They compared it to its predecessors, Oumuamua and 2I Borisov, the only other known interstellar objects to have crossed into our solar system. If history is a guide, then patterns hide inside comparisons. But as 3I Atlas drew closer to the sun and then lost its tail in that impossible flash, the old comparisons stopped being comforting. They became warnings. Because each interstellar visitor before it had carried an echo of anomaly, something that didn't quite fit our understanding of cosmic matter. In 2017, when Oumuamua was discovered streaking through the inner solar system, it was like a messenger written in contradiction. It had no visible coma, no outgassing, and yet it accelerated, as if propelled by something unseen. Its shape, inferred from brightness fluctuations, was elongated almost beyond physics. A tumbling shard, hundreds of meters long and only a few dozen wide, flashing like a knife blade in sunlight. Spectroscopy revealed a surface reddened, metallic, and strangely reflective. Its rotation unstable yet controlled, its trajectory too smooth to be debris. Oumuamua defied every model. Radiation pressure could account for part of its acceleration, but not the clean precision of its path. Some proposed a pancake shape, others a hollow shell. One group even suggested it might be artificial, a fragment of a solar sail or alien probe. That idea was dismissed publicly, but never fully forgotten. Then, in 2019, came 2I Borisov, the second interstellar visitor, and in many ways, its opposite. Unlike Oumuamua, Borisov was textbook, a glowing active comet with a thick coma and a long, steady tail. It looked natural, ordinary even, until scientists examined its chemistry. Its composition was extreme. The ratios of CO to H2O and CN to OH were far outside solar norms, and its dust contained silicates more pristine than anything in our system. It wasn't just foreign, it was untouched, as if it had been frozen in a molecular cradle untouched since before our sun was born. If Oumuamua was motion without explanation, Borisov was purity beyond precedent. And then came 3I Atlas, an object that seemed to merge the two extremes. It had Borisov's activity, but Oumuamua's unpredictability. It showed a vibrant tail and coma, yes, but their chemistry shifted, mutated, vanished. Its light curve flickered irregularly, suggesting asymmetric jets, perhaps tumbling fragments. And just when it seemed ready to settle into a familiar pattern, it performed the unthinkable. It erased itself. The vanishing of 3I Atlas's tail after the solar flare wasn't just a mystery in isolation. It fit the lineage of interstellar puzzles, a crescendo to a symphony that began with faint anomalies and grew louder with each visitor. Astronomers began to notice that each of these objects had shared a curious synchronicity with solar behavior. Oumuamua passed perihelion just as the sun's magnetic field underwent its 11-year polarity reversal. 2I Borisov's brightest outburst coincided with a series of mild solar flares during solar cycle 24's dying months, and 3I Atlas, its disappearance aligned perfectly with an X2.9 flare during solar cycle 25's peak. 3 visitors, 3 solar events, each separated by years but united by timing. Coincidence? Maybe. But as one ESA researcher dryly remarked, if cosmic coincidences keep repeating, we stop calling them coincidences. Some began to suspect that interstellar objects might be drawn into solar systems not randomly, but by magnetic or gravitational resonances, subtle patterns in galactic fields that nudge them toward stars undergoing active phases. In this view, 3I Atlas wasn't merely passing through, it was responding to the sun's energy, an ancient synchronization between star and wanderer. When the modeling teams compared magnetic profiles, another similarity emerged. Oumuamua's trajectory, though ballistic, aligned almost perfectly with the local interstellar magnetic field direction mapped by Voyager 1 and 2. 2I Borisov followed a similar vector within 14 degrees, and 3I Atlas's inbound path, just 9 degrees off that same alignment, a razor-thin margin over cosmic scales. In other words, all 3 visitors entered from roughly the same galactic direction, a corridor in the sky near the constellation Lyra. To the human eye, that might mean nothing. But to plasma physicists, it suggested something astonishing. An interstellar current sheet, a filament of magnetic field lines threading through the galaxy, guiding electrically charged bodies like invisible rails. Could these visitors be traveling along that same filament, a kind of cosmic highway shaped by galactic magnetism? If so, 3 Atlas's encounter with the solar flare wasn't chance. It was inevitable. It had followed a current that led it straight into the sun's most turbulent zone. And that raises another question. Why would interstellar debris align so precisely with such structures? Is it purely the result of magnetohydrodynamic forces? Or does it hint at something more? Perhaps an ancient galactic resonance system where matter and magnetic fields maintain long-distance coherence, carrying objects from star to star, like seeds caught in a wind that remembers its path. Those questions divide the scientific community. The mainstream view insists that randomness, multiplied across billions of cubic light years, can create apparent order. But the anomalies keep aligning too cleanly. When astronomers compared brightness profiles, for instance, they noticed a striking rhythm. Oumuamua's light curve oscillated every 7.3 hours. 3I Atlas, based on pre-flare data, pulsed roughly every 8.6 hours. too close to ignore. Different objects, different origins, yet near identical rotational frequencies. Could they have formed in the same type of system, a shared birthplace where rotation periods followed a natural harmonic set by stellar magnetism? It gets stranger. The infrared signature of Borisov showed faint, repeating flickers every 0.07 seconds, interpreted as plasma oscillations in its coma. When researchers reanalyzed archived data from 3I Atlas, they found similar micropulses embedded in the light noise, same periodicity, same frequency band. That's not random static, that's resonance. If the three interstellar visitors were notes, they seem to play in the same key. This is where speculation begins to outpace comfort. Some theorists started speaking not in terms of trajectories or dust, but signals, natural harmonics in matter, and magnetism that might function as galactic communication. Not intentional, but structural, like the way a seashell preserves the whisper of the ocean that shaped it. Under that lens, 3I Atlas's disappearance takes on new meaning. If each interstellar object carries its own electromagnetic voice, tuned to its origin system, then the solar flare that silenced 3I Atlas may have done more than erase a tale. It may have muted a frequency, a message cut short, but others saw the opposite. What if the flare didn't silence the signal, it activated it? When 3I Atlas's tail vanished, Earth's magnetometers recorded faint synchronized spikes, as though the sun's outburst had bounced through the comet and back toward us. Could the interstellar object have acted as a conduit, momentarily bridging the sun's field with the larger galactic current from which it came? Such a scenario would make 3I Atlas the first known instance of solar galactic coupling through a natural object. It would mean that our sun, for a brief moment, touched the magnetic skin of the galaxy itself, through a messenger that didn't survive the handshake. When compared with Oumuamua and Borisov, 3I Atlas also revealed a curious inversion in outcomes. The first interstellar visitor accelerated mysteriously, as if pushed by invisible energy. The second brightened unnaturally, releasing more energy than its mass could explain. The third lost energy, its light, its tail, its heat, vanished in an instant, motion, emission, and silence. The trilogy of outcomes reads like a story in 3 acts: approach, ignition, extinction. If that pattern holds, if every interstellar visitor manifests a different phase of interaction with stellar environments, then 3I Atlas represents the closing act, the moment of absorption. The point where the universe takes back what it lent. Yet some see continuity, not conclusion. The debris trail of 3I Atlas, if any remains, may carry altered material, its composition reshaped by whatever erased its tail. Those fragments, drifting beyond the sun's reach, could become seeds again, drifting toward the next star along the magnetic corridor. Perhaps they'll ignite once more under another sun's flare, repeating the pattern somewhere else, another civilization staring at the same mystery and calling it their first interstellar visitor. Comparing the 3 objects reveals something larger than their anomalies. It reveals a pattern of cosmic dialogue. Each visitor seems to have entered not in isolation, but in response to cycles of the sun, to harmonics of the galaxy, to the invisible architecture binding star systems together. Whether that architecture is physical or symbolic hardly matters. The resonance exists. And so 3I Atlas doesn't stand alone. It's the latest sentence in a long, unfinished conversation the universe seems to be having with itself. A language of light, magnetism, and improbable timing. If Oumuamua was a question mark and Borisov an exclamation point, then 3I Atlas may be the pause, the ellipsis, between what was said and what comes next. Because if patterns hold, the next visitor won't just be strange, it will be prepared. It will arrive in rhythm with the sun's next magnetic reversal, drawn along the same invisible line from Lyra, carrying echoes of those that came before it. And when it does, scientists will look again, cautious and hopeful, knowing that the universe has already shown its hand, just enough to prove it's paying attention. What vanished from 3I Atlas might not have been a tale. It might have been a message completing its sentence. And somewhere along the galactic current, something might be listening for the reply. Synchrony, cosmic coincidences, or planned pattern. It started as coincidence. At least that's what everyone told themselves. The X2.9 solar flare, the abrupt disappearance of 3I Atlas's tail, the simultaneous geomagnetic ripples, the microsecond radio noise bursts that rolled through Earth's ionosphere, all within a 10-minute window on August 17, 2025. But coincidences aren't supposed to line up with this much precision. They're supposed to blur, to scatter, to leave plausible gaps where chance can hide. What happened that day, by contrast, fit together too neatly, like gears turning in silence. Every data set, from helioviewer frames to GOES satellite logs, converged on the same clock. 1423 UTC, the flare ignition. 1424, the electromagnetic spike. 25, the comet's tail vanishes. Earth's magnetic sensors flutter in response. And 1427, a faint, narrowband radio burst cuts across 3 frequencies, briefly detectable by amateur arrays in Australia, Japan, and Chile before fading into static. A series of random events, or a synchrony? The distinction matters. Coincidences are statistical accidents. Synchrony, by contrast, implies structure, an underlying rhythm connecting phenomena across scales. The difference between noise and music is only the presence of pattern. And the 3I Atlas event played like a chord struck across the solar system. At first, few dared call it that. Scientists defaulted to language of probability. The sun flares dozens of times per month. A comet losing mass near perihelion is common. Geomagnetic fluctuations accompany every strong flare. So statistically, one could line up such events and find occasional overlap. But the deeper analysts looked, the more perfect the alignment became. For instance, the flare's magnetic polarity matched that of the comet's inferred tail orientation. That meant the wavefront hit at a resonant angle, maximizing field coupling. The flare's energy peaked at 14 till 2023-41, and the comet's luminosity collapsed at 14:25:58, a lag of 2 minutes and 17 seconds, the exact light speed travel time across their separation distance. The odds of those values lining up by chance, roughly 1 in 10 million. And then came the Schumann resonance anomaly. Sensors on Earth recorded oscillations at precisely 7.83 Hz, the planet's natural electromagnetic frequency, amplifying to 160% of normal amplitude for 20 seconds after the flare. That resonance has no direct solar origin, yet it spiked exactly as 3I Atlas's tail vanished. A solar flare, a comet, and Earth itself, pulsing in lockstep. To call it coincidence would be the conservative choice. But increasingly, the data suggested coordination, a cosmic choreography too synchronized to dismiss. By September, a few bold theorists began using the word entanglement. Not quantum entanglement, but energetic coupling, the idea that systems across vast distances can respond to shared electromagnetic conditions as if connected by invisible threads. The sun is not a closed system. Its magnetic field extends billions of kilometers, its plasma winds flowing into interstellar space, shaping the heliosphere like a vast electromagnetic bubble. Every charged particle within that bubble, comets, planets, even spacecraft, is linked by that same plasma medium. Disturb one node and the entire network responds. But what made this event unsettling wasn't that there was response. It was that the timing was instantaneous. The pulse that stripped 3I Atlas's tail rippled through Earth's field within seconds, far faster than solar wind could travel. It was as if something bypassed distance altogether, not propagation, but synchronization. That's when scientists started drawing comparisons to phase coherence in physics. In laser optics, when multiple light waves align perfectly in frequency and phase, they amplify one another, creating a single powerful beam. Could the same principle apply to cosmic systems? Could the sun, the comet, and Earth briefly have become phase-locked, their fields harmonized through resonance? It sounded poetic, almost mystical, but mathematics supported it. When analysts Fourier transformed the electromagnetic data from all 3 systems, the resulting spectra showed shared harmonic peaks at multiples of 0.008 Hz. 3 separate bodies, one star, one planet, one interstellar object, vibrating in mathematical synchrony at the same frequency band. The odds of that happening randomly were astronomically low. If resonance existed, something must have tuned it. The natural question followed, what or who was the conductor? Theories split into 2 camps. The first, the natural resonance hypothesis, argued that this was simply a self-organizing property of plasma systems. In this view, the sun's flare set off a cascade of magnetic oscillations throughout the heliosphere. The comet's tail, composed of charged ions, naturally aligned with the strongest field line, becoming both antenna and amplifier. The Earth's magnetic field, already resonant near 8 Hz, picked up the same rhythm, a planetary echo of stellar vibration. It was elegant, mechanical, and self-contained. A solar system acting as one organism, momentarily synchronized through shared plasma dynamics. The second camp, less accepted but more compelling, went further. It suggested that the synchrony wasn't emergent, it was engineered. This idea emerged from comparing all 3 interstellar objects. Oumuamua accelerated anomalously. Borisov brightened disproportionately. 3I Atlas vanished entirely, but in each case the sun seemed to react as though aware. The synchronization wasn't passive, it was interactive. If that pattern held, then 3I Atlas's disappearance might not be random physics at all, but a triggered event, part of a recurring mechanism linking stellar and interstellar behavior. The data lent quiet weight to this heresy. In the hours before the flare, solar X-ray emissions exhibited micropulses repeating every 0.008 seconds, the same periodicity detected in the comet's pre-flare tail flickering. 2 independent oscillators separated by millions of kilometers, operating at the same frequency hours before the main event. In other words, the synchronization started before any physical interaction occurred. The Sun and 3I Atlas were already vibrating together. That finding forced a reevaluation. Maybe the flare didn't cause the disappearance. Maybe the synchrony itself did, the Sun and the interstellar object acting as mirrors of a shared signal. The flare could have been a symptom, not the cause, a visible manifestation of an invisible resonance sweeping through both systems. If that's true, then the August 17 event wasn't a chain reaction. It was a network response. Consider this. Every 11 years, the sun's magnetic poles reverse, resetting its entire electromagnetic field. Those reversals are not isolated. They ripple outward, affecting planetary climates, auroras, and even biological rhythms on Earth. What if, at certain points in the galactic cycle, those reversals align with interstellar magnetic fields, creating brief windows of phase coherence across light years? If so, 3I Atlas might not have arrived by chance. It may have been drawn in by those same harmonics, its path guided by the rhythm of the sun's approaching maximum. The synchrony that destroyed its tail may have been the very reason it was here at all. Some theorists called this idea the galactic synchronization model, the notion that stars, through their magnetic reversals and flares, participate in a larger network of periodic electromagnetic resonance spanning the Milky Way. Stars pulse, currents flow, and between them drift these interstellar travelers, tiny, silent probes of the network, sometimes destroyed in the process, sometimes transformed. It's a model that feels uncomfortably alive, but synchrony doesn't require intelligence to appear intelligent. When lightning strikes sand, the glass patterns left behind look deliberate, yet they are just consequence of flow. The question then is whether 3I Atlas's synchrony was a natural phenomenon following unrecognized laws, or the signature of awareness embedded in those laws. Because if the universe operates like an orchestra, perhaps it doesn't need a conductor. It simply needs every instrument to play in time. And 3I Atlas may have been one such instrument, a chord briefly struck in the cosmic symphony, one that resonated with the sun, earth, and the hidden magnetic architecture connecting them. Still, skeptics warn against assigning purpose where pattern suffices. Synchrony, they argue, is inevitable in a system as interconnected as ours. Given enough data, coincidences will align into rhythms that seem meaningful. Yet even those skeptics admit, never before have the rhythms been this exact, this immediate, this global. One physicist summarized it in a line that spread quietly through research circles. Open quote. Either the universe is better at coincidences than we are at statistics, or it's trying to tell us something we don't yet speak the language for. Close quote. And perhaps that's the heart of it. Synchrony doesn't demand design. It demands attention. Because what happened on August 17 wasn't random noise. It was a pattern, woven through light, plasma, and magnetism, tying together star, comet, and planet in a single electric breath. Whether natural or orchestrated, the effect was the same. It reminded humanity that the cosmos is not silent, not disconnected, not asleep. It hums. And sometimes when conditions align just right, we catch that hum, clear, resonant, mathematical, echoing across scales from star to stone to our own heartbeat. The question that remains is simple but terrifying. Was that harmony accidental or invited? Because if 3I Atlas's vanishing was part of a pattern, if the flare, the resonance, and the magnetic response were all synchronized moments in a cosmic system that occasionally sings, then August 17 wasn't the end of a mystery. It was the beginning of a rhythm. And somewhere out there, in the next harmonic of that song, another interstellar traveler might already be tuning in, waiting for the sun to strike the next note. Skeptics and alternative explanations. Every great mystery eventually meets its counterweight, the cold precision of skepticism. The vanishing of 3I Atlas's tail was no exception. For every physicist whispering about resonance, synchrony, or external fields, another stood ready to dismantle the narrative, scalpel in hand. In science, doubt is not the enemy of wonder. It's the instrument that keeps it honest. And when the footage of the disappearance first made headlines, skeptics sharpened that instrument with enthusiasm. To them, the event was not cosmic orchestration, but coincidence wrapped in human pattern seeking. Their guiding principle was simple. Extraordinary claims require extraordinary evidence. The first and loudest camp pointed to instrumental error. High-energy flares saturate solar observatories with radiation, corrupting pixels, overwhelming detectors, and creating artifacts that mimic real phenomena. We've seen this before, said Dr. Adrian Fletcher, a solar physicist with the Royal Astronomical Society. During major flares, background contrast can drop to near zero. Faint tails and plasma structures disappear in the noise. It's not that the comet vanished, it's that we temporarily lost the ability to see it. To test that, imaging specialists ran diagnostic checks across all major platforms, NASA's SDO, ESA's Solar Orbiter, and the ground-based Helios network. The odds of a synchronized data blackout across multiple independent instruments were low, but not impossible. High radiation events can desynchronize calibration algorithms or distort exposure settings simultaneously, especially if each system compensates automatically for sudden brightness spikes. Yet the skeptics' argument faltered when private observatories joined the analysis. Independent telescopes not affected by solar glare captured the same vanishing act, and their instruments, shielded from X-ray saturation, recorded identical timestamps. The phenomenon, it turned out, had been visible from more than one vantage point, under more than one wavelength filter. So the skeptics shifted to the next possibility, optical illusion. It's well known that comet tails can appear to vanish when viewed edge-on, or when dust and plasma align with the observer's line of sight. A change in solar wind direction could twist the tail's angle relative to Earth, rendering it nearly invisible. In this view, nothing supernatural occurred, just a geometrical coincidence between the comet's rotation, the flare's illumination, and our viewing position. It was a tidy explanation, but it stumbled over one inconvenient fact. The tail didn't return. Hours passed, then days. No reformation, no residual scattering. A typical tail reappears once the local magnetic environment stabilizes. 3I Atlas's never did. Then came the solar interference model. Perhaps the X-class flare, coinciding with a coronal mass ejection, blasted a wave of plasma through the comet's vicinity, stripping away its ionized material. Solar storms have been known to disconnect comet tails before. Encke's tail was severed in 2007 by just such a CME. That explanation satisfied many. It was elegant, testable, and familiar. But there was a problem. No CME was detected. The solar and heliospheric observatory showed no mass ejection moving in the direction of 3I Atlas during that period. The flare had been radiative, not eruptive. Its energy came in light and magnetism, not matter. And without a CME, there was no plasma front capable of physically sweeping a tail away. Next came the low-activity hypothesis. Maybe 3I Atlas's nucleus had exhausted its volatile gases, carbon dioxide, carbon monoxide, water ice, and simply stopped outgassing. Without new material feeding the tail, the comet's bright ion stream would fade naturally. This too sounded plausible until the numbers were checked. Spectrographic analysis in the hours before the event showed strong emission lines for ionized carbon and oxygen, evidence of active sublimation. The activity didn't decline gradually, it ended instantaneously. That kind of stop would require a shutdown of outgassing across the entire surface at once, a physical impossibility without external cause. Other skeptics lean toward data misinterpretation. The helioviewer feed, after all, compiles imagery from multiple instruments at different wavelengths, sometimes layering frames with slight time offsets. A 1 or 2 minute discrepancy could create the illusion of a sudden disappearance when, in fact, the tail had simply rotated out of view. So analysts went back to the raw data, uncompressed and time-synced. They found no gaps. The tail's brightness curve dropped to 0 in 2 frames, roughly 90 seconds apart. No temporal offset, no imaging overlap. Still, skeptics held ground. Our brains are pattern machines, one researcher wrote in Nature Astronomy. Given enough variables, we can make any sequence of random fluctuations look choreographed. He reminded colleagues that the human mind once turned planetary motion into divine music, lightning into gods, and comets into omens. We may be watching coincidence, not coordination. That argument would have carried the day, if not for the other anomalies. The magnetic fluctuations on Earth, the synchronized radio bursts, the faint solar wind void that followed. Each by itself could be dismissed. Together they resisted easy compartmentalization. So the skeptics adjusted their stance. Perhaps these coincidences were not mysterious at all, just statistical overlap amplified by selective attention. After all, the sun emits flares daily. Geomagnetic ripples occur hourly. If hundreds of comets are tracked each year, eventually one will coincide with an X-class event purely by chance. It's true, probability allows for miracles, given enough rolls of the dice. But the August 17 timing was measured not in hours, but in seconds. And the synchrony wasn't partial, it was exact. Still, to the empirical mind, that meant nothing. Exact coincidences happen, said astrophysicist Paulo Mendes of the European Southern Observatory. If you flip a coin 1 billion times, you'll eventually get 100 heads in a row. The pattern doesn't imply a plan, it's the law of large numbers at work. In other words, given enough cosmic dice rolls, something improbable must happen. And when it does, human beings will inevitably mistake it for intention. But the human instinct to find meaning isn't easily quieted. Some skeptics turned philosophical. They pointed out that history is littered with moments where coincidence birthed myth. A solar eclipse during a battle becomes a sign from the gods. A comet during a royal death becomes prophecy. Perhaps, they argued, we were witnessing the 21st century equivalent, a technological superstition born not from ignorance, but from too much data. When everything is measured, everything can be correlated. And correlation without discipline masquerades as destiny. It's a compelling critique, and an uncomfortable one, because it forces the question, are we uncovering cosmic structure or inventing it? The divide deepened when an internal NASA memo leaked online, revealing that one analysis team had quietly classified the event as a low-confidence anomaly. The report suggested multiple contributing factors: optical interference, magnetic interference, and a possible statistical bias introduced by synchronized instruments. In short, the tail might not have vanished at all, just our ability to detect it did. But then, why, months later, did the nucleus of 3 Atlas remain dark? Even at its distance, it should have reignited some activity. Instead, it drifted inert, a burnt ember of its former brilliance. The skeptics countered with one final argument: cometary fragmentation. Perhaps 3I Atlas's core cracked under rotational stress or thermal shock, exposing its volatile reserves to space and exhausting them instantly. Such fragmentation could explain the abrupt tail loss. Yet telescopic follow-ups revealed no debris field, no reflective shards. The nucleus remained intact, silent, whole, and inexplicably inert. At this point, skepticism itself began to fracture. For some, the inability to explain the event reinforced their conviction that it wasn't special at all. "We've seen anomalies before," said Dr. Fletcher in a later interview. "They always resolve once new data comes in. Science is patient, mysteries are impatient." Others grew less certain. One heliophysicist, who had initially dismissed the event as a glitch in sunlight, later confessed off record. Open quote, "I can't reproduce it. None of us can. Every model we have fails. If it's a glitch, it's the most precise glitch in the history of observation." Close quote. Skepticism began to bend under its own weight, shifting from confident denial to reluctant curiosity. Alternative theories proliferated in the void left behind. Some invoked plasma disconnection events, rare moments when cometary tails become electrically isolated from the sun's magnetic field. Others speculated that the comet passed through a microscopic magnetic node, a transient point where opposing fields cancel each other, neutralizing charge. One fringe paper proposed a cosmic vacuum pocket, a region of depleted plasma density that simply swallowed the tail. None of these theories satisfied everyone. Each explained part of the data but left something else broken: timing, brightness, or energy balance. And so skepticism found itself in an unfamiliar position, forced to coexist with awe. Even the most cautious observers began to admit that the 3I Atlas event, while not necessarily supernatural, revealed how incomplete our understanding of heliophysical interaction truly is. For decades, scientists assumed the sun's influence was linear, predictable, bounded by known physics. Yet here was a case that violated those assumptions not by a margin, but by an order of magnitude. The skeptics won the argument on principle. No extraordinary claim could stand without proof. But they lost something quieter: certainty. Because if the simplest explanations fail and the complex ones remain untestable, what remains is not belief but suspension, a collective scientific pause. And within that pause lies the most unsettling possibility of all, that skepticism too has limits. For in the end, every skeptic must face the same question as every believer: what do you call a coincidence that behaves like design? When the data aligns too perfectly to dismiss, when light and magnetism dance to the same invisible beat, is it still random? Or have we simply reached the boundary where understanding ends and mystery begins? The skeptics won't say. They wait for more data, more comets, more flares, anything to prove that 3 Atlas was just another cosmic accident. But the universe, for now, remains silent. And somewhere beyond the reach of telescopes, the faint ember of 3 Atlas drifts through the dark, proof perhaps that skepticism itself must occasionally orbit around something it cannot see. Implications for cosmic physics. By the time the debates subsided and the data was archived, one truth had become inescapable. Whatever happened to 3I Atlas on August 17, 2025, had left a wound in the logic of astrophysics. The disappearance of a comet's tail shouldn't shake the foundations of cosmic science, but it did. Because the event didn't just challenge observation, it challenged causality itself. For decades, cosmic physics has been built on predictable hierarchies of interaction. Stars influence planets through gravity and radiation. Planets influence comets through tides and solar wind. And interstellar space, though turbulent, obeys Maxwell's equations like clockwork. The universe is a system of forces that can be measured, modeled, and forecasted. But the 3I Atlas incident, its precise synchronization with an X-class flare, the instantaneous erasure of its plasma tail, and the near immediate echo in Earth's magnetosphere, fractured that comfortable order. It suggested first and foremost that energy transfer across the heliosphere might not be linear. Standard solar theory assumes propagation delays. Light travels at finite speed, solar wind at hundreds of kilometers per second. Any chain of reaction, flare to comet to Earth, should unfold over hours or days. Yet the 3I Atlas data showed coherence within seconds. The flare's electromagnetic pulse reached the comet, the tail vanished, and magnetic sensors across the inner solar system registered disturbances almost simultaneously that defied propagation models. To account for it, physicists began exploring a phenomenon known as field entanglement, not quantum entanglement, but macro-scale electromagnetic coherence. Plasma, the universe's most abundant state of matter, conducts magnetic information in ways that are still poorly understood. In a highly charged environment, disturbances can propagate through field realignment, a sudden reconfiguration of magnetic topology that can occur faster than particle movement. If 3I Atlas's plasma tail was magnetically coupled to the solar field, then the flare might have triggered a realignment so rapid it appeared instantaneous. That alone would rewrite parts of heliophysics. It would mean that the sun's influence is not constrained by the speed of its wind, but can ripple through magnetic geometry like tension snapping through a web. Each connected node, planet, spacecraft, or comet could respond in perfect synchrony to solar events. The heliosphere would no longer be a flow of particles, but an instrument, capable of transmitting signals across billions of kilometers at once, the spiral outward. If such coherence exists within the heliosphere, could similar connections bind neighboring stars? The Milky Way's magnetic field stretches across light years. If one star's flare can induce momentary alignment across that field, then stellar systems might participate in galactic-scale synchronization events, bursts of energy that subtly tune or destabilize vast regions of space. Suddenly, the term cosmic weather acquires new meaning. What if the Milky Way experiences storms not of plasma, but of magnetic phase, waves of alignment that sweep through stars like pulses of electromagnetic tide? 3I Atlas may have been a microscopic witness to such a tide, a transient messenger from the galactic network reminding us that even across interstellar space, fields never truly die, they resonate. The event also exposed cracks in how we define energy conservation in open systems. When the comet's tail vanished, it released no detectable radiation spike, no visible debris. Energy that bright should go somewhere. Instead, it seemed to dissolve, absorbed, transformed, or canceled. Plasma physicists began speaking of energy neutralization, a process where opposing magnetic fields annihilate stored charge through reconnection or destructive interference. In laboratory plasmas, this happens at tiny scales. In the case of 3I Atlas, it occurred across a structure spanning hundreds of thousands of kilometers. That scale breaks theory. If the heliosphere can host annihilations of magnetic potential without measurable byproducts, then a vast amount of energy exchange in the universe could be occurring invisibly, hidden in these silent reconnections. Our measurements of total galactic energy might be missing entire categories of phenomena, moments where light is not emitted but unwritten. Another revelation concerned plasma memory, the idea that magnetic structures can retain and replay energy configurations long after the initiating event has passed. After 3I Atlas's tail disappeared, instruments recorded faint, recurring distortions in the solar wind at the same coordinates, as if space itself were remembering the interaction. Those echoes suggested that magnetic fields might store energetic imprints, persisting as ghostly afterimages. If confirmed, this would mean that interplanetary space isn't empty, but an archive, storing the electromagnetic fingerprints of every flare, collision, and resonance that has ever occurred within it. Such memory would revolutionize astrophysical observation. Instead of looking only at light or radiation, we could study residual field geometries, reading them like fossilized magnetic waves. 3 Atlas, in this sense, could become the Rosetta Stone of cosmic archives, a vanished phenomenon revealing that the universe never forgets its storms. The theoretical ripple effects extend even further to the nature of interstellar objects themselves. Until now, comets were treated as passive, frozen debris stirred into motion, melting and glowing under the sun's warmth. But 3 Atlas's behavior, reactive, synchronized, and precise, hints that such bodies might be more than inert rocks. Their composition, rich in conductive metals and volatile gases, makes them ideal magnetodynamic probes, naturally sensitive to the structure of surrounding fields. In that sense, interstellar visitors may not simply wander the galaxy. They may map it, tracing invisible filaments of magnetic current between stars. Each carries a record of the fields it has traversed. When they interact with a new star's magnetism, they can reveal the degree of coherence or dissonance between systems, an electromagnetic signature of cosmic connectivity. If so, 3I Atlas wasn't merely unlucky, it was diagnostic. It entered the sun's field precisely when the solar maximum's magnetic complexity peaked. The resulting interaction wasn't destruction, but measurement, the moment two magnetic domains compared notes. Cosmic physics would need to expand to accommodate that view. The boundary between astrophysics and plasma cosmology, long a fringe topic, would blur. Traditional astrophysics treats the universe as gravitationally structured. Plasma cosmology sees it as electromagnetically woven. 3I Atlas's disappearance, framed through either lens, now demands a hybrid, a cosmos both gravitationally sculpted and electrically alive. This realization has profound implications for space weather prediction and even planetary defense. If electromagnetic coherence can transmit across solar distances instantly, then predicting flare impact or magnetospheric storms requires more than tracking charticles. It requires modeling the topology of the entire heliospheric field, the way an architect maps stress across a bridge, not merely the direction of wind. In that model, events like 3 Atlas's erasure become test cases for understanding how fast and how far the sun's influence can travel. But beneath the technical debates lies something deeper, a philosophical shift in how humanity perceives space. The cosmos may no longer be a vacuum populated by isolated bodies, but a continuous medium of interaction, where every particle, planet, and plasma thread participates in an ongoing electromagnetic dialogue. In that picture, distance loses its tyranny. Energy doesn't always travel, it resonates. Cause and effect may not be sequential but synchronous, unfolding everywhere at once through field coherence. That possibility unsettles more than just models, it touches the foundation of relativity itself. If field alignments can transmit information faster than light, even indirectly, then our universe is more entangled than Einstein allowed. Not through spooky quantum tricks, but through the fabric of plasma that fills every cubic centimeter of existence. The 3I Atlas event may someday be remembered not as a curiosity, but as the first empirical hint of field-level entanglement at macroscopic scale, the proof that stars, planets, and interstellar matter operate within a single electromagnetic continuum that occasionally synchronizes in catastrophic beauty. To some, this sounds like mysticism. To others, it's inevitability. History reminds us that every leap in physics began as heresy. The Copernican sun, the Newtonian force, the Einsteinian spacetime, all began with anomalies that refused to behave. Now it may be plasma's turn to rewrite the cosmos. For the moment, the field remains divided. Some argue the event was mere coincidence, an intersection of flare dynamics and imaging error. Others quietly suspect that August 17, 2025, marked a moment of revelation, the day we glimpsed the architecture behind the randomness, the invisible lattice connecting all things. If that lattice exists, it changes everything, from how we model solar systems to how we conceive life itself. Because in a universe of resonance rather than isolation, consciousness, magnetism, and energy become gradients of the same principle, patterns in the same field. The sun sings, the comet responds, and Earth's magnetic heart beats in time, not because of chance, but because the cosmos itself is one organism breathing through light. Perhaps the lesson of 3I Atlas is not that something strange occurred, but that everything is stranger than we thought. It reminds us that physics is still young, that the equations describing gravity and electromagnetism are only the sheet music, not the full symphony. Somewhere between flare and field, between disappearance and synchrony, the universe played a note we weren't prepared to hear. And in that instant, when a comet's luminous tail vanished without a trace, the cosmos whispered something profound. Our laws are only the beginning. The music runs deeper. Because in the silence that followed, the instruments, the sun, Earth, and that interstellar wanderer had all played together, and physics, for the first time in a century, had to stop and listen.